All right, let's dive deep into some pretty intense math today. We're talking open-closed Deligne Mumford field theory, specifically the kind associated with the Lagrangian submanifold.
Yeah, definitely a mouthful.
And we're going way beyond the usual surface level stuff here. You send over that HIRSCHI and Hoffer paper. Looks like we're getting into cutting-edge research.
Absolutely.
Builds on all that Lagrangian flower theory and Fukaya category stuff, right?
Right. It's all connected. And what I think is really cool is this theory is dealing with enumerative invariants, which are based on bordered curves with, and this is the key, Lagrangian boundary conditions. I mean, anyone who's worked in this area knows those Lagrangian boundary conditions introduce a whole new level of complexity.
Yeah, not exactly an easy stroll in the park.
Yep.
Especially when you throw in the whole non-orientability of the moduli spaces.
Exactly.
So HIRSCHI and Hoffer, they're like our Sherpas guiding us through this mathematical Everest.
You could say that.
What makes their approach so groundbreaking?
Well, for a long time, people have been struggling to define these open Gromov-Witten invariants in higher genus. They were okay in genus 0, with the disk.
Yeah, the good old disk.
But once you get to higher genus, like a torus or something with multiple holes, things get really messy. Defining these invariants becomes almost impossible.
Okay, I'm starting to see why this is a big deal.
Yeah.
But maybe we should rewind for a second.
Okay.
Can you remind us what open Gromov-Witten invariants actually are? Even back in grad school, I struggled with this concept.
Sure. So imagine you have a symplectic manifold. Think of it as the space with a special geometric structure.
Okay, got it.
And inside this manifold, there's a Lagrangian submanifold. Now, these open Gromov-Witten invariants, they're basically counting these specific types of maps from what we call bordered curves into this symplectic manifold. The tricky part is the boundary of these surfaces. It has to stay on that Lagrangian submanifold.
So it's like you're mapping a piece of paper onto a curved surface, but the edges of the paper are glued to a specific line on that surface.
That's a great way to picture it. Now, in lower genus, like with a disk, things are relatively well behaved. But when you move to higher genus, these moduli spaces, which is where all these maps kind of hang out, the boundaries of those spaces get incredibly complex.
Ah, so it's like the difference between navigating a smooth sphere and like a jagged mountain range.
Perfect analogy. And that's where HIRSCHI and Hoffer come in with their global Kuranishi charts.
Okay, let's unpack those global Kuranishi charts. They were always a bit of a headache for me. How do they help us out here?
So think of a Kuranishi chart as a local coordinate system for these crazy moduli spaces. What HIRSCHI and Hoffer do is they create a way to stitch all these local charts together, like you're putting together a really complicated puzzle to get this global picture of the entire moduli space.
Okay, I'm following so far.
Now, in the closed case, with those nice closed curves, these charts are pretty manageable. But with these open curves, the boundaries start causing all kinds of problems. They introduce corners and all these complicated boundary structures into the charts. So what HIRSCHI and Hoffer figured out, their breakthrough, was how to construct these global Kuranishi charts specifically for open stable maps. And that's absolutely crucial for defining the invariants in higher genus.
Okay, so they've managed to tame these wild moduli spaces with these Kuranishi charts. But you mentioned something earlier about a problem with orientation.
Yeah.
That's always been a major roadblock in this area, hasn't it?
Absolutely. These moduli spaces, they can be non-orientable.
Right. It's like trying to define clockwise and counterclockwise on a Mobius strip. Just doesn't work.
Exactly.
And if you don't know which way is up, you can't really count anything meaningfully. So how do they deal with this non-orientability issue?
This is where things get super interesting. HIRSCHI and Hoffer, they actually worked out the orientation signs for these moduli spaces, which no one had ever done before for open stable maps in higher genus.
Wow, that's impressive.
It is. And they build upon the work of Chen and Zinger, who developed a way to construct orientations in similar settings.
So by tackling these orientation signs head-on, they basically cleared another major hurdle in defining these higher genus invariants.
Exactly. And this is a big step towards their ultimate goal, which is constructing an open-closed Deligne Mumford field theory.
Okay, time for the main event. I've heard these field theories whispered about in hushed tones, but what exactly are they? And why is constructing one such a big deal?
Well, in a nutshell, a field theory, it gives us this framework for understanding the algebraic structure that's kind of embedded in certain geometric objects. It's like a mathematical language for describing patterns and relationships in these spaces.
I'm listening.
So in this specific case, the open-closed Deligne Mumford field theory. It captures the algebraic relationships within the moduli spaces of open stable maps. And this specific field theory, it actually comes from Gromov-Witten theory, which deals with invariants associated with closed curves.
So it's like a bridge between the world of closed curves and the world of bordered curves.
Exactly. It takes this well-established theory of Gromov-Witten invariants and extends it to include those crazy bordered curves with their Lagrangian boundary conditions.
That's pretty remarkable. But how do they actually go about building this field theory? What are the basic ingredients?
It's a multi-step process. Each step is pretty intricate. First, they introduce something called the Novikov ring, which is a fancy way of saying a formal power series ring. This helps them keep track of the energy of the curves. And then, of course, there are those global Kuranishi charts we talked about earlier. Those provide the scaffolding for the whole construction.
So Novikov ring keeps tabs on energy. Kuranishi charts provide the map. What else is involved?
Well, they also have to make sure their construction actually follows the rules of the game. They have to prove that it satisfies a set of axioms, which are basically like the fundamental principles for how these geometric objects should behave.
Makes sense. They're putting together this really complicated puzzle here. But I'm a bit lost on this Novikov ring. What does it mean to keep track of the energy of the curves?
It's kind of like assigning a weight to each curve based on its geometric properties.
Okay.
So the energy in this context is related to something called the homology class of the curve in the target space.
Okay.
And this ring structure, it's really important for defining the operations of the field theory, which are basically ways of combining and manipulating these curves.
So it's not energy in the physics sense, but more like a way to categorize and differentiate between these curves.
Exactly. It's a bookkeeping tool that helps them keep everything organized and make sure they're accounting for all the different types of curves.
Okay, I'm getting a clearer picture now. They've tackled these higher genus invariants, built these global Kuranishi charts, and brought in the Novikov ring for energy bookkeeping. Sounds like they've laid a pretty solid foundation for their open-closed field theory.
They have, and that's just the beginning. Their work goes on to explore all the details of the moduli space, how those invariants are actually calculated, and a whole lot more.
So now we get to the real nitty-gritty of the math.
Yeah, the fun part. We'll be digging into their analysis of those orientation signs, how they deal with different types of maps in the moduli space, and how they ultimately prove that their construction satisfies all the necessary rules for a well-defined field theory.
This is where I really get to flex my mathematical muscles. I'm ready to dive in.
Great. So we've been talking about how HIRSCHI and Hofer tackled this problem of defining open Gromov-Witten invariants in higher genus.
Right, with those global Kuranishi charts and their whole approach to orientation.
Exactly. But now let's really get to the heart of their work, constructing the open-closed Deligne Mumford field theory.
Yeah, let's get to the main event. I'm especially interested in this concept of a Tom system, which you mentioned before.
Right.
It seems crucial to their whole construction, but to be honest, it's a little fuzzy in my memory.
The Tom system is really the key to everything they do. It's a specific toolkit designed to solve a very particular problem.
And that problem is?
Integration over moduli spaces. Remember, those moduli spaces, they're not usually smooth manifolds. They could have corners, edges, all kinds of weird singularities.
So like trying to calculate the area of a surface that's all crumpled and folded up.
Perfect analogy, and that's where the Tom system comes in. It's like a mathematical iron, smoothing out those wrinkles so you can actually integrate over these spaces.
Okay, that makes sense. So how do they create this mathematical iron? What are the components of the Tom system?
Well, the foundation is those global Kuranishi charts we talked about. They break the moduli space down into these manageable pieces.
Right, like dividing a complex problem into smaller, solvable chunks.
Exactly. Now, the Tom system assigns a special differential form to each of these charts. Think of it as a measuring tool that's tailored to each local part of the moduli space.
Differential forms. I vaguely remember those from my topology days. A quick refresher.
Sure. Basically, differential forms let you describe the geometric and topological properties of a space in a way that lets you do calculus on it, specifically integration.
Okay, so they're assigning these mathematical measuring tools to each Kuranishi chart.
Right.
But it can't just be any random forms, right?
Right. The important thing is, these differential forms, which together make up the Tom system, they have to have specific compatibility properties.
I see.
When you glue those different parts of the moduli space back together, those forms have to stitch together perfectly.
Like a really complex jigsaw puzzle, where each piece has to fit exactly with its neighbors.
Exactly. And that compatibility is crucial because it ensures that the integration theory they define is consistent and makes sense.
Okay, so far so good. They break down the space, assign these special forms, make sure they fit together smoothly. But how do they actually use those forms to integrate over the whole space?
This is where it gets really clever. Instead of integrating directly over the messy, singular moduli space, they use a trick. They pull back the integration process to the smooth Kuranishi charts, where things are much easier to work with. It's like calculating the area of a bumpy surface by first flattening it out.
So they simplify the problem by working on those nice smooth charts and then translate the results back to the whole space.
Exactly. They integrate on each chart separately and then push forward those results back to the full moduli space, taking into account how all the charts fit together and using those compatibility properties of the forms.
Like stitching together individual pieces of fabric, making sure the seams line up to measure a whole garment.
Great analogy. And this whole process, the Kuranishi charts, the special forms, it all culminates in being able to define those crucial numerical invariants. The invariants are the key to understanding the geometry and topology of these moduli spaces.
So they've built this TOM system. They can integrate, they can calculate these invariants. Sounds like a pretty solid foundation for their field theory.
It is. But it doesn't stop there. They also showed that their construction satisfies certain axioms, these fundamental rules that ensure the theory is consistent and logically sound.
Right, those axioms are like the building codes that ensure their mathematical structure is sound.
Exactly. Verifying those axioms is essential because it shows their theory isn't just some isolated thing, but it connects to the bigger picture of mathematics.
Can you give us a quick example of one of these axioms and how they actually verified it?
Sure. One of the most important is the gluing axiom. It basically says that when you glue together two bordered curves along a boundary, the invariant of that combined curve is equal to the product of the invariants of the original curves. Like saying, if you join two pieces of land, the total area is the sum of the original areas.
Sounds pretty intuitive. But I imagine the math behind it is not so simple.
You're right. It's not trivial at all. To prove it, HIRSCHI and Hofer had to really dig into the details of the COM system. They show that their integration process works properly with this gluing procedure and that the invariants behave correctly.
So they weren't just waving their hands and saying, trust us, it works. They provided a rigorous mathematical proof.
Exactly. And that's what makes their work so impressive. They're not just proposing a theory, they're backing it up with solid mathematical reasoning. And their verification of the gluing axiom, along with all the other axioms, shows how robust and consistent their construction is.
This attention to detail and rigor is really impressive. They've laid a solid foundation for other researchers to build upon. It makes me wonder, are there any open questions that their work raises? What are the next steps in this area of research?
Oh, absolutely. Their work opens up so many new avenues to explore. One question that really stands out is whether their techniques can be extended to even more general situations.
So like they've built a working model, and now the challenge is to see how we can adapt it to handle even more complex tasks.
That's a great way to put it. And this is what's so exciting about research. Their work is a starting point for so many future investigations, and it could lead to some really profound discoveries.
I can't wait to see what the future holds for this field. It feels like we're just scratching the surface. You mentioned earlier that their work connects to things like mirror symmetry and Lagrangian cobordisms. Can you tell us more about those connections?
Of course. Mirror symmetry, as we talked about, is this amazing duality that connects different geometric worlds. HIRSCHI and Hofer's work, even though it's not directly about mirror symmetry, it gives us the tools to start exploring these dualities in a whole new way.
So it's like they've given us a new way to decode the messages hidden within these geometric structures.
Precisely. Their framework could help us understand these mirror relationships and see connections that we never noticed before.
And what about Lagrangian cobordisms? How does their work shed light on those?
Remember, Lagrangian cobordisms are these higher dimensional objects that connect different Lagrangian submanifolds.
Right, like bridges between those submanifolds.
Exactly. And HIRSCHI and Hofer's work gives us a way to study how open Gromov-Witten invariants change as you move along these cobordisms.
So we can track the evolution of these invariants as we travel between different submanifolds.
Exactly. And that has some really deep implications for understanding the Fukaya category, which is this powerful tool for organizing the relationships between Lagrangian submanifolds.
It sounds like their work is giving us a whole new perspective on some of the most fundamental concepts in symplectic geometry and algebraic topology.
It really is. And it's not just limited to those areas either. Their work could have an impact on all sorts of fields, from knot theory to string theory, and even theoretical physics. It's a great example of how interconnected mathematics really is.
It's been amazing exploring the depths of HIRSCHI and Hofer's work with you today. We've gone from the basics of open Gromov-Witten invariants to the complex details of their Tom system and the verification of the axioms. And we've even gotten a glimpse of all the exciting possibilities that their research opens up. It's a major contribution to the field, and I'm really eager to see what comes next.
I couldn't agree more. It's been a pleasure discussing this with you. And it's work like this that reminds us why we love math in the first place. The beauty, the power, the endless potential for discovery.
Welcome back. We've been on quite a journey with this open-closed Deligne Mumford field theory.
It's pretty amazing stuff.
It is. We've talked about how HIRSCHI and Hofer's research opens up all these new ways of understanding things like mirror symmetry and Lagrangian cobordisms.
Right.
But now I'm ready to get into the nitty-gritty. Let's talk about that Tom system, the actual mathematical machinery behind it all.
Let's do it. It's one thing to understand the concept, but to really appreciate it, you have to see how it works.
Exactly. So as a reminder, what problem does the Tom system solve?
Integration over moduli spaces. And the reason it's a problem is those spaces are generally not smooth manifolds. They're all bumpy and jagged with corners and edges and singularities.
Like trying to measure the area of a crumpled up piece of paper.
Exactly. The Tom system is like this mathematical iron that smooths out those wrinkles so you can actually do integration.
Okay, I can picture that. So how do they create this iron? What's in the Tom system toolbox?
Well, remember those global Kuranishi charts we talked about?
Yeah, those were key.
They decompose the moduli space into these manageable chunks, like breaking down a big problem into smaller, more solvable ones.
So they're using those charts as a guide to navigate this complex moduli space.
Precisely. And then the Tom system, what it does is it assigns this special differential form to each of those Kuranishi charts. Think of it as a measuring tool that's specifically made for that particular piece of the space.
Differential forms, yeah, those always sounded a bit mysterious to me.
Yeah.
Can you give us a quick explanation of what they are and why they're important here?
Sure. Differential forms, basically they're a way of encoding the geometry and topology of a space in a way that lets you do calculus on it, integration and all that.
Okay, so they're assigning these measuring tools to each of the charts. But they can't just be any random forms, right?
Oh, no. The key thing is that these differential forms, which make up the Tom system, have to have specific compatibility properties. When you glue those different parts of the moduli space back together, the forms have to stitch together seamlessly.
It's like those really complex wooden puzzles, where each piece fits perfectly with its neighbors to make the whole picture.
That's a perfect analogy. And that compatibility is essential because it makes sure the integration theory they define actually works and makes sense.
Okay, I see how it fits together now. They break down the space, they assign these special forms, they make sure everything fits together smoothly. But how do they actually use these forms to integrate over the whole moduli space? There's still a gap there for me.
Right. This is where it gets really clever. Instead of trying to integrate directly over that messy moduli space, they use this trick. They pull back the integration process to those smooth Kuranishi charts. It's like if you want to measure the area of a bumpy surface, you first flatten it out and then measure the flat pieces.
So they simplify the problem by working on those nice smooth charts.
Yeah.
And then they translate the results back to the full moduli space.
Exactly. They do the integration on each chart separately where it's much easier, and then they push forward those results to the whole space. And they do all this very carefully, taking into account how the charts are glued together using the compatibility properties of those forms.
It's like stitching together individually measured pieces of fabric, making sure all the seams line up perfectly to get an accurate measurement for the whole garment.
That's a great analogy. And all of this, the Kuranishi charts, the special forms, it all leads to defining those crucial numerical invariants. The invariants are like the key to unlocking the secrets of these moduli spaces.
So they've built this elaborate Tom system. They can integrate over these crazy moduli spaces, and they can calculate those invariants. It sounds like a solid foundation for their field theory.
It definitely is. But their work doesn't stop there. They go even further, showing that this whole construction satisfies those important axioms, those fundamental rules that make sure the theory is consistent and connects to other areas of mathematics.
Right, those axioms are like the building codes that ensure their mathematical structure is sound.
Exactly. And verifying those axioms is essential because it shows that this theory isn't just some abstract idea, but a real part of the mathematical world.
Can you give us an example of what these axioms are like, and how do they go about actually verifying them?
Sure, let's take the gluing axiom, which we talked about earlier. This axiom says that when you take two bordered curves and glue them together along a boundary, the invariant of that new combined curve should be the same as if you multiplied the invariants of the original curves together. It's like saying if you combine two pieces of land, the total area should be the sum of the original areas.
Intuitively, that makes sense, but I'm guessing the math isn't quite that simple.
You're right, proving it is quite a feat. HIRSCHI and Hoffer had to really dig into the mechanics of the TOM system to prove it. They had to show that their integration process works correctly with this gluing procedure and that the invariants behave as expected. Their proof involves a lot of clever geometry and intricate analysis.
So they're not just relying on intuition here, they're providing a rigorous, step-by-step mathematical argument.
Exactly. And that's what makes their work so strong. They're not just saying, hey, this is a cool idea. They're providing a solid mathematical foundation for it.
This level of detail is really impressive. It lays the groundwork for others to build upon. And it makes me wonder, are there any open questions that their work raises? What's next in this area of research?
Oh, absolutely. Their work opens up so many new questions and possibilities. For example, one big question is whether their techniques can be extended to even more general situations. They've shown that these higher genus open Gromov-Witten invariants exist in a certain context, but can we generalize their construction to include a wider range of symplectic manifolds and Lagrangian submanifolds?
So it's like they've given us this working prototype, and now the challenge is to see how we can tweak it and modify it to do even more.
That's a perfect analogy, and that's what makes research so exciting. There's always more to explore, more to learn, more to discover.
Well, this has been an incredible journey, exploring the depths of HIRSCHI and Hoffer's work with you. We've gone from those basic concepts of open Gromov-Witten invariants to the intricate machinery of their TOM system and the rigor of their proofs. And we've even glimpsed some of the vast possibilities that their research opens up. It's clear that their work is a major contribution to the field.
I completely agree. It's been a real pleasure delving into this with you. And I think work like this is a great reminder of why we're all so fascinated by mathematics. The beauty, the power, the endless potential for discovery. It's truly inspiring.
And to everyone listening, thank you for joining us on the deep dive. We'll see you next time. All right, diving into open-closed Deligne Mumford field theory today. Some pretty dense papers, gotta say.
Yeah.
I'm really interested in these algebraic structures behind open stable maps.
Yeah.
Especially in higher genus.
Yeah, it's a rich area, lots to unpack. And the tools. Global Kuranishi charts, TOM forms. Pretty powerful stuff.
For sure. And I think what makes this open setting so interesting is the challenge it poses. Like, we've had success with enumerative invariants for closed curves and closed manifolds, but introduce boundaries, things get a lot trickier.
Oh, absolutely. That non-orientability of moduli spaces, it's a major hurdle in the open setting. Imagine trying to consistently assign an orientation to a surface that's, well, not simple, twisting and turning, and then the boundaries just add another layer of complexity. It's not always possible.
And this isn't just some theoretical mathematical quirk, right? This non-orientability has real implications for fields like symplectic geometry and string theory.
Exactly. Big implications, like in symplectic geometry. Understanding these open invariants could give us whole new perspectives. And in string theory, these open curves could represent the world sheets of open strings, fundamental to the theory.
Okay, so let's get specific. What exactly are we talking about when we say open stable maps?
Okay, picture this. Maps from a rim and surface, but here's the key, with boundaries. And these maps go into our symplectic manifold. But the boundaries, they're not just hanging out there. They get mapped to a Lagrangian submanifold. And the stable part, that makes sure these maps behave, even when things get complex. Multiple components, nodes, places where the surface intersects itself, it's all got to be well behaved.
So we're not talking about your simple everyday curves here. We're allowing for some really intricate shapes.
Oh, for sure. Intricate is the word. And to really study these open, stable maps, we need to understand the spaces they live in, the moduli spaces. These spaces, they parameterize all the possible variations of these maps, and they have a lot going on. Geometric structures, algebraic structures. It's fascinating. And one of the papers we're looking at today, it dives deep into understanding these structures in higher genus, which means more holes in our surfaces, more complexity.
Okay, and this is where things start to get really interesting. One paper brings up Costello's work on open-closed topological conformal field theories, TCFTs.
Yeah.
How do those connect to what we've been talking about?
TCFTs, they give us this great framework for studying how strings interact in all sorts of different configurations. Costello's work, what it shows is how, if you focus on a specific operad, the operad of disks with boundary punctures, you can actually get an ACAR category from a TCFT.
Okay, got to pause there for a second. What exactly is an operad in this context?
All right, think of an operad like this. It's a collection of operations, but with rules. Rules for how you can put them together, compose them. In this case, the operations are all about gluing disks together along their boundaries. And the punctures, those are marked points on the boundaries. Like, think of them as places where open strings can attach.
Ah, okay. So we study how these disks with punctures are glued together, and that tells us something about how open strings interact.
Exactly, that's the idea. Costello's work bridges the gap between these TCFTs and the algebraic structures we find in those moduli spaces of open, stable maps.
Yeah, things are starting to get a little mind-bendy here. Let's move on to another tool you mentioned. Global Kuranishi charts. What are they, and why are they important?
Okay, so moduli spaces. They can be pretty complicated to work with. Global Kuranishi charts, they're like maps to help us navigate that complexity. They let us represent these spaces locally as the zero set of a section of a vector bundle over a smooth manifold. And that means we can use tools from differential geometry to study them.
So it simplifies things in a way.
It does. But there's a trade-off. These charts, they can have corners, boundary strata, which makes defining orientations and integrals tricky. It all has to be considered very carefully.
Which brings us back to that challenge of non-orientability.
Full circle.
Right.
And this is where theorem B comes in. This theorem gives us a way to construct these global Kuranishi charts, specifically for open stable maps. It's a big step, a concrete tool to analyze these spaces, even when they're non-orientable.
Okay, and I see the paper also mentions relative spin structures. How do those factor into defining orientations?
Relative spin structures, they're essential. If we want to establish orientations for these moduli spaces, they give us a way to assign a notion of, well, spinning to the fibers of the vector bundle, even when the base space isn't orientable. And the paper gets very specific. It details the exact choices of integers that we need to define the auxiliary data for these global Kuranishi charts so that the orientations are well defined.
All right, so we've got these charts. We're figuring out how to orient them. What's next?
Well, those charts, they can have boundary strata. So to get a global picture of the moduli space, we need to understand how those pieces are connected. And that's where clutching maps come in.
Right. These maps describe how we glue the components of the moduli space together along those boundaries.
Precisely. And the paper dives into the different types of clutching maps we see in this setting, and really importantly, how to figure out their orientation signs.
Why are those signs so important?
They tell us whether the orientations of the pieces we're gluing, they match up. If we get those signs wrong, well, then we run into problems. Defining things like integrals over the moduli space becomes a mess.
So it's all about making sure everything fits together, seamlessly, consistently.
Exactly. And the paper really gets into the details of how to calculate these orientation signs for all these different clutching maps, which is a pretty big technical accomplishment.
Now, I've seen the terms pre-gluing and anti-gluing pop up. What are those techniques used for?
Those are all about analyzing what happens when we try to glue stable maps, whose domains are nodal curves. So curves that have these self-intersection points. Pre-gluing, it's like we're creating approximate solutions to the Cauchy-Riemann equations, the ones that govern these maps, by smoothing out those nodes. And anti-gluing, it does the opposite. It breaks apart a smooth map into the components that correspond to the different parts of that nodal curve.
So we're zooming in and out, in a way, looking at the behavior of the map at different levels of detail around these nodes.
Exactly. And these techniques, they tie right back into the global Kuranishi charts. The paper explains how pre-gluing and anti-gluing are used to thicken these charts, creating the smooth space that contains our original moduli space. as a subspace.
Why do we need to thicken the charts? What's the purpose of that?
It lets us use the tools from differential geometry. Even when the moduli space isn't so well behaved, it might not be orientable, or it might have singularities. Thickening gives us a nice, smooth space to work with. And then we can relate our findings back to that original moduli space.
Okay, this is starting to make a lot more sense, but let's bring it back to the big picture. Deligne Mumford field theory. How does everything we've talked about connect to that?
Right, so Deligne Mumford field theory, it's this big framework for studying enumerative geometry problems, specifically in Gromov-Witten theory, which is all about counting curves in symplectic manifolds.
So it's a way to quantify the geometric information we're trying to understand.
Exactly. And the paper we're talking about today, it defines an open-closed Deligne Mumford field theory that's specifically associated with the Lagrangian submanifold. And this lets us calculate these invariants, these numbers that capture important geometric information for open, stable maps, the ones with boundaries on that Lagrangian submanifold.
Now, you mentioned the Novikov ring earlier, which sounds pretty technical. What's its role here?
It's essential because when we're calculating these invariants, we end up with these infinite sums. Remember, our moduli spaces, they can have infinitely many curves. So the Novikov ring, it gives us a rigorous way to deal with those infinities, mathematically speaking.
So like a special accounting system for infinite quantities.
Perfect analogy. Without the Novikov ring, we wouldn't be able to define these invariants in a meaningful way.
Okay, so just to recap, we're using these global Kuranishi charts, Thom forms, the Novikov ring, to build this open-closed Deligne Mumford field theory. And the goal is to extract meaningful geometric information from these moduli spaces of open, stable maps. Did I get that right?
You got it. That's a great summary. And the paper goes all in. It explains exactly how to construct this theory, using all the tools we've talked about. And it proves that it actually satisfies the axioms of a Deligne Mumford field theory. A big result.
Okay, we have covered a lot of ground, but let's go back to Thom forms for a minute. What exactly are they, and how do they fit into all of this?
All right. Thom forms, they're these special differential forms. They represent something called the Thom class of a vector bundle. And what they let us do is integrate over the fibers of that vector bundle, which is crucial for defining the cooperations in our field theory.
Hold on, cooperations. Can you expand on those a bit?
Oh, right. So these are like the core operations in our Deligne Mumford field theory. They encode the gluing of curves, and they tell us how to combine invariants from different components of the moduli space when we glue those components together.
So Thom forms are like the glue that holds these cooperations together.
I like that. That's a good way to think about it. And the paper gets into the specifics, the compatibility conditions that these Thom forms need to satisfy, and how we use them to define those cooperations. It's a great example of how all these different mathematical pieces come together to solve a complex problem.
Now, the paper talks about this idea of doubling, relating the moduli spaces of open stable maps to the moduli spaces of closed stable maps, which we understand a lot better generally. Can you explain that a little?
Yeah, it's a cool trick. Basically, imagine you take your surface, the one with boundaries, and you glue a mirror image to it. So you end up with a closed surface. No boundaries. That's doubling. The paper describes a doubling map. Sends the moduli space of open stable maps to the moduli space of closed stable maps, but with a specific real structure. And this allows us to use what we already know about closed curves to understand the open case.
So we're kind of embedding these open stable maps into a larger space of closed maps by doubling them. But why is this real structure so important?
It's what makes this embedding work. The real structure makes sure that the doubled map is compatible with the involution on CPN, the one that fixes RPN. Basically, it guarantees that the glued mirror image behaves the right way during the doubling process.
Makes sense. But how do we actually construct these global Kuranishi charts for the moduli spaces of open stable maps? The paper mentions a few things: polarizations, auxiliary data, good coverings.
It's a multi-step process. First, we need a polarization. Think of it like choosing a line bundle on our symplectic manifold, one that satisfies some positivity conditions. This helps us define a notion of energy for our stable maps.
Energy, like from physics.
Exactly. It's a way to quantify the size or complexity of the maps. Next, we need auxiliary data. Things like an almost complex structure, a way to measure angles and orientations on our manifold, a good coupling of the moduli space, and a connection on the tangent bundle.
So it's like gathering all the right ingredients to set the stage for building these charts.
Yeah, exactly. A good covering lets us break down the moduli space into smaller, more manageable pieces. And the connection. That gives us a way to transport vectors along curves on the manifold.
Okay, but how do these tools actually come together to build the charts?
All right, now it gets a little more technical. We use the auxiliary data to construct a section of a vector bundle over a thickened version of the moduli space, carefully chosen.
Thickening again. Seems like we're doing a lot of that.
It's really important. The thickening gives us this smooth space. That contains our original moduli space as a subspace. And, here's the key, the zero set of the section we construct. That's precisely the original moduli space.
So the global Kuranishi chart, it's basically a map from this smooth space to our moduli space. And it captures the essential structure of the moduli space.
Exactly, that's the idea. And the paper explains how to choose the right auxiliary data to make sure this construction works, even when we're dealing with those non-orientable moduli spaces.
It's pretty amazing that whether these moduli spaces are orientable or not, it actually depends on choices we make during this construction process.
Absolutely. The paper gets into how the specific choices of integers that we use to define the auxiliary data, they actually determine the orientability of the resulting global Kuranishi charts. It's a really delicate problem, and it shows how important it is to have this rigorous framework for making these decisions.
The paper mentions that orientability isn't always guaranteed in the open setting, which is different from the closed setting. It suggests that there's this fundamental difference between open curves and their moduli spaces.
That's a really key observation. Those boundaries in the open setting, they bring a whole new level of complexity. In the closed setting, there are often these natural ways to orient the moduli spaces. But in the open setting, we have to be much more careful.
And the paper highlights the importance of relative spin structures for establishing these orientations. Could you say more about that?
Sure. A relative spin structure, it's like a way to lift the structure group of our vector bundle from the general linear group to a spin group. And this lets us define a consistent notion of spinning on the fibers of the bundle, even when the base space, our thickened moduli space, is not orientable itself.
Spinning. Now that's where my intuition starts to break down.
It is pretty abstract. Think of it this way. A spin structure lets us assign a sign, plus or minus, to each point in the moduli space in a consistent way. And these signs are what allow us to define a well-defined orientation.
So it's like we're adding this extra layer of information to the moduli space, this spinning information to help us orient it, even when it's all twisted and turning in these complex ways.
That's a great way to visualize it. And the paper proves this big theorem, Theorem B. It shows that if we equip our Lagrangian submanifold with a relative spin structure, then we can orient those global Kuranishi charts in a canonical way.
A pretty big result.
Yeah.
It gives us a concrete way to tackle this problem of orientability. And the paper also goes into how these orientations behave when we glue different Kuranishi charts together.
Right. Those clutching maps we talked about before, they don't just glue the charts together, they also affect the orientations. The paper analyzes the orientation signs of these clutching maps very carefully and shows how those signs depend on the choices we made when we defined the relative spin structures.
So it's not enough to just orient each chart individually. We have to make sure the orientations are compatible when we glue them together.
Exactly. And the paper goes through and proves a whole series of lemmas, describing the exact orientation signs for different types of clutching maps. So we have a really complete picture of how these orientations behave under gluing.
Really impressive work, the way they tackle these complex problems with such precision. So let's move on to the actual definition of the open-closed Deligne Mumford field theory.
Okay, so the goal here is to construct a framework. That lets us calculate invariants. These are numbers that capture important geometric information for open, stable maps, the ones with boundaries on our Lagrangian submanifold.
And the paper defines this field theory as a functor, from a certain category of decorated moduli spaces of open, stable curves to the category of chain complexes over the Novikov ring.
It sounds abstract, but it gives us a way to associate algebraic objects, chain complexes, to our geometric objects, the moduli spaces. And the Novikov ring, like we talked about earlier, that lets us handle the infinite sums that pop up when we calculate these invariants.
So we're kind of translating geometry into algebra using chain complexes and the Novikov ring to express this geometric information.
Exactly. And the fact that this is a functor, it makes sure that it respects the gluing of curves. What that means is that the algebraic objects associated with glued curves, they're related in a specific way. to the algebraic objects associated with the individual components.
So it's not just some random assignment of chain complexes to moduli spaces. There's a structure there that reflects the geometry of the gluing process.
Exactly. And the paper goes to great lengths to show that this construction satisfies all the axioms of a Deligne Mumford field theory, which is a big deal, mathematically speaking.
Now, how do we actually get those invariants? The numbers that tell us something meaningful about the geometry of these open, stable maps?
This is where those cooperations come in. Remember, they encode how we glue curves, and they're defined using those Tom forms. By integrating these Tom forms over certain cycles in the moduli spaces, we get our invariants.
So it's like using those cooperations as probes to extract specific bits of information from these moduli spaces, which can be really vast and complex.
That's a great way to put it. The paper proves this key theorem. It shows that these cooperations satisfy the axioms of a cohomological field theory, which is a special type of Deligne Mumford field theory, and that ensures that the invariants we calculate, they're well-defined and meaningful.
Okay, it's really all starting to connect now. But before we go on, can we talk a bit more about the compatibility conditions for those Tom forms?
Yeah.
They're what ensure a smooth transition when we glue different charts together, right?
Exactly. They're essential if we want to make sure the cooperations are well-defined, and that the invariants we calculate, they don't depend on the specific choices we made during the construction process. It highlights how important it is to be really careful and pay attention to detail in mathematics.
The paper also talks about this idea of relative smoothness. Where does that fit into all of this?
It's a really important technical point. Remember, those moduli spaces, they can have corners, boundary strata. They can get pretty complicated. Relative smoothness gives us a framework to handle those complexities in a rigorous way.
So it's a way to extend the usual ideas of smoothness and differential forms to these more general spaces.
You got it. It lets us define things like tangent spaces, differential forms, integration on these moduli spaces, even when they're not smooth manifolds in the usual sense.
And why is that so important?
Because it's what allows us to define and work with the objects we need to construct this Deligne Mumford field theory. For example, those Tom forms we talked about, they're defined as relative differential forms, and the cooperations involve integrating these Tom forms. So we need a well-defined notion of integration on these moduli spaces.
So relative smoothness is kind of the foundation. That makes all of this higher-level math possible.
That's a great way to put it. It gives us the language and the tools to talk about smoothness and calculus on these complex spaces, which is crucial for understanding everything else.
Now, I noticed that the paper has a separate section on the unstable range. What's that all about?
That's where things get a little more complicated when we're dealing with curves that aren't stable, meaning they have too many automorphisms. In those cases, we need to adjust our constructions to make sure everything stays well-defined.
So there are special rules for handling these unstable curves.
Yep, exactly. And the paper carefully analyzes these unstable cases, defines these modified corporations, and proves that they still satisfy the necessary axioms.
I'm sensing a theme here. Careful analysis. Attention to detail. It's all crucial to make sure everything is rigorously defined and that the theory actually works as expected.
You're absolutely right. That's what good mathematics is all about. Every step has to be justified. Every potential problem has to be addressed. This paper is a great example of how to build a really complex theory with both elegance and rigor.
Before we move on to the last part, is there anything else you want to emphasize about this section of the paper?
Yeah, I think it's important to really highlight the paper's discussion of those orientation signs. Remember, those signs are critical for making sure that the orientations of different charts match up when we glue them together. And the paper goes into a lot of detail, analyzing those signs. For all sorts of different clutching maps, it shows a really deep understanding and a commitment to mathematical rigor.
It's really impressive how much attention is paid to those orientation signs for the clutching maps. It seems like a small detail, but it really impacts the consistency of the whole theory.
Absolutely, yeah. If we mess up those signs, the orientations won't match up when we glue the charts together, and the whole framework falls apart. We could end up with invariants that don't make sense.
Like trying to force puzzle pieces together that are the wrong way around. They might fit, but the picture's all messed up.
Exactly. The paper does a really thorough job of making sure those signs are calculated correctly, considering all the different possibilities.
It's amazing how they systematized it. Clear rules for determining the orientation signs.
Yeah, that's the power of math, right? Find the underlying structure, the relationships, and even the most complex things start to make sense.
So we've got the charts. We know how to orient them. We know how to glue them together without messing up the orientations. What's the next step in building this open-closed Deligne Mumford field theory?
Well, remember, the goal is to define this field theory associated with our Lagrangian submanifold, and that means constructing a functor, one that assigns chain complexes to our moduli spaces of open stable maps.
And that functor has to satisfy certain axioms, right, to be a real Deligne Mumford field theory.
Right, and the paper, it defines this functor very carefully, and then it goes through and proves rigorously that it satisfies all the axioms. It's a really thorough piece of work.
Can you give us a high-level overview of how this functor is constructed?
Sure. Basically, it involves taking the chain complex of relative differential forms on our thickened moduli space and twisting it by the orientation line bundle, which makes sure that those orientations we worked so hard to define are actually incorporated into the algebraic framework.
So we're translating the geometry into algebra. Chain complexes capture the information about the moduli space, including the orientation.
Exactly. And because this is a functor, it means it respects the gluing of curves. So the chain complexes that we associate with glued curves, they have a specific relationship to the chain complexes associated with the individual components.
It's all starting to feel like a very intricate, well-organized system. The moduli spaces, the Kuranishi charts, conforms, orientation signs, chain complexes, they all fit together.
It's a beautiful theory, and the paper really lays it all out, step by step.
Let's go back to the Novikov ring for a second. Why is that so important in all of this?
Well, remember when we calculate those invariants, we end up with infinite sums, because those moduli spaces can have infinitely many curves. The Novikov ring is what makes those infinite sums make sense, mathematically speaking.
Like a way to keep track of infinite amounts.
Yeah, exactly. Without it, the invariants wouldn't be well-defined.
Okay, so we built this whole machine, this open-closed Deligne Mumford field theory, using all these complex tools and ideas. Now, how do we actually use it to extract those invariants, those numbers that tell us something about the geometry?
Ah, that's where the cooperations come in. They tell us how to glue curves together, and they're defined using those Thom forms. If we integrate those Thom forms over certain cycles in the moduli spaces, we get our invariants.
So the cooperations are like probes. We use them to pull out specific geometric information from these moduli spaces.
I like that analogy. And the paper proves this theorem. It shows that the cooperations actually satisfy the axioms of a cohomological field theory, which is a special type of Deligne Mumford field theory. And that means the invariants we get are well-defined. They make sense.
It's all very impressive. This whole deep dive has been really insightful. I feel like I've learned a lot.
Yeah.
But it's also raised even more questions for me.
That's how it always is with research, right? The more we learn, the more we realize there is to explore. And this area, it's full of possibilities.
Before we wrap up, what would you say is the most significant takeaway from this work?
I think it's important to remember that this isn't just abstract mathematics. It has the potential to really change how we understand physics, specifically string theory. If we can understand open-closed Deligne Mumford field theories better, we might make real breakthroughs in understanding space and time, the fundamental forces of the universe.
That's an incredible thought. It makes you wonder what other connections and applications might be out there just waiting to be discovered.
Exactly. And with that, maybe it's time to end our deep dive for today. We've explored this fascinating world, open-closed Deligne Mumford field theories, unpacked some key concepts, seen how powerful these tools are. Now it's up to you to keep exploring.
Who knows what we'll discover next? Welcome to the deep dive. Today we're really going deep into some fascinating mathematics.
Oh, yeah.
Exploring a new theory connecting geometry and topology and quantum field theory. We're focusing on a paper titled An Open-Closed Deligne Mumford Field Theory Associated to a Lagrangian Submanifold.
Okay.
Sounds complicated.
Yeah.
Don't worry, we'll unpack it all.
Exactly. We'll be your guides through this complex world of moduli spaces and open stable maps and Gromov-Witten invariants.
From what I understand, this new theory builds on ideas from Lagrangian flower theory and the Fukaya category.
Right.
It seems mathematicians have been grappling with these concepts for a while,
Yeah.
trying to create a solid framework for enumerative invariants in open settings. curves with boundaries.
That's right.
Mm.
There were some major roadblocks, like dealing with non-orientability of moduli spaces and tricky codimension 1 strata.
Right.
The paper highlights workarounds from mathematicians like Welschinger, Liu, and Nerjivo, who tackled specific cases.
Yeah.
But a general solution remained elusive.
So this paper aims to provide a more comprehensive approach.
It does. It focuses on a specific scenario, a Lagrangian submanifold within a symplectic manifold.
Okay.
But even within this framework, the math gets incredibly intricate, especially as you move to higher genus curves
Right.
with multiple boundary components.
Okay. I'm ready to dive in.
Let's do it.
Let's start by breaking down the core concepts.
Okay.
What exactly is an open-closed Deligne Mumford field theory,
Right?
and why is it important?
Well, the name might sound like a mouthful,
Yeah, it does.
but it's actually quite descriptive once you break it down.
Okay.
To understand it, you first need to grasp the concept of an open-closed topological conformal field theory, or TCFT for short.
TCFTs. I've encountered those before,
Right.
but a refresher would be great.
Okay.
Remind me, how do they come into play here?
Imagine you have a moduli space of bordered curves.
Well,
These are essentially surfaces with boundaries, like a disk or an annulus. Now, in a TCFT, you have chains on these moduli spaces, acting on chain complexes.
So we're taking these geometric objects, these curves with boundaries,
Right.
and associating them with algebraic structures.
That's a great way to put it.
Yeah.
And these TCFTs provide a powerful way to understand the geometric and topological properties of spaces
Right.
by studying how these chains interact.
Interesting. But how do these TCFTs connect to the broader mathematical world?
Yeah.
Where do HEF categories fit into all of this?
HAF categories provide a framework for understanding objects and their relationships.
Okay.
Think of it like a map of a city where objects are buildings and relationships are the roads connecting them.
Okay.
TCFTs can be understood within this framework,
Yeah.
allowing us to classify and study them more systematically.
Okay, I see. So we've got these TCFTs acting on chain complexes,
Right.
and we're trying to understand them through the lens of HEF categories.
Yeah, exactly.
But how does this all lead to the open-closed Deligne Mumford field theory specifically?
Think of an open-closed Deligne Mumford field theory as a particular type of open-closed TCFT. It's a framework that connects several different mathematical areas,
Okay.
including string topology and cobordism categories.
Hold on. String topology. Now we're talking about loops and manifolds.
Right.
How does that relate to curves with boundaries?
You're right to point out that connection. In string topology, we study the space of loops in a manifold, and these loops can be seen as closed curves.
Yeah.
But in the open-closed setting, we're also interested in paths that start and end at different points,
Right.
which can be represented by curves with boundaries.
So we're essentially expanding our scope to include both closed loops and open paths.
That's it.
And you mentioned cobordism categories.
Yes.
How do those fit into the picture?
Cobordism categories deal with ways to connect different Riemann surfaces,
Okay.
particularly the idea of gluing them together along their boundaries.
Right.
This gluing operation is crucial for understanding how different pieces of our moduli spaces fit together.
Okay, this is starting to make sense. But I have to admit, I'm still a bit hazy on the formal definition of an open-closed Deligne Mumford field theory.
Okay.
Can you walk me through that?
Of course. Formally, it's defined as a symmetric monoidal functor,
Okay.
from a cobordism category to the category of chain complexes.
Whoa, a what functor?
A functor.
That sounds pretty abstract.
Yeah.
Can you break that down a bit for me? I'm pretty good with functors.
Sure.
But I think our listeners might need a little help here.
Sure. Think of a functor as a machine
Okay.
that takes objects and relationships from one category
Right.
and translates them into objects and relationships in another category,
Okay.
all while preserving their structure. In this case, our machine takes cobordisms, which are ways to connect different Riemann surfaces,
Okay.
and translates them into operations between chain complexes.
Right.
It's like a dictionary that translates geometric concepts into algebraic ones.
So we're taking geometric operations like gluing surfaces together
Yes.
and turning them into algebraic operations between chain complexes?
Yeah.
Speed. That's pretty mind-bending.
It is. Now, within this theory,
Yeah.
we have a couple of key players.
Okay.
First, there's the closed state,
Okay.
which is a particular chain complex associated with a closed string or a closed curve in our manifold.
Right.
And then there's the chain complex associated with Lagrangian submanifolds,
Okay.
which represent our open strings or curves with boundaries.
Okay, so we're bringing together these open and closed aspects of these geometric objects
Yes.
within this algebraic framework.
That's right.
But how do mathematicians actually work with these concepts in practice?
Right.
It all seems very abstract.
That's where global Kuranishi charts come in.
Okay.
Imagine you're trying to study a complicated multidimensional object.
Okay.
It would be helpful to have a set of coordinates to navigate it, right?
Like a map for a complex terrain?
Exactly. That's what Kuranishi charts provide for moduli spaces.
Okay.
They give us local coordinate systems, allowing us to describe and understand these abstract spaces.
So these charts are like our mathematical GPS for navigating these moduli spaces.
That's a pretty good analogy. And one of the key achievements of this paper is the construction of global Kuranishi charts for open, stable maps.
Right.
This means we now have coordinate systems that work consistently across the entire moduli space, even when dealing with these open curves with boundaries.
That sounds like a significant breakthrough.
Yeah.
But haven't there been challenges in applying Kuranishi charts in the past?
Oh, yeah.
Especially when it comes to open curves.
Yeah.
Don't those pesky boundaries throw a wrench into things?
You're absolutely right. One of the biggest hurdles has been dealing with corners that appear in the global Kuranishi charts.
Yeah.
When we introduce open curves, unlike closed curves, which give us nice, smooth moduli spaces, these open curves create corners, making the geometry much more intricate to handle.
Yeah.
This paper delves into the analysis of these boundary strata and how they affect the structure of the moduli space.
So it's like we're adding extra dimensions to our map.
Yeah.
Making it much more complex to navigate.
Exactly.
I'm beginning to understand why this problem has been so difficult to crack.
Precisely. But the authors of the paper provide some clever tools and techniques to handle this added complexity.
Right.
Now, another crucial aspect we need to discuss is orientability.
Okay, orientability.
Yes.
So we're talking about having a consistent notion of direction, right?
Yes.
Like knowing which way is up on these moduli spaces.
Right.
I remember that being important for defining invariants in other contexts.
You're exactly right. Orientability is essential for defining those invariants, which are the mathematical quantities that help us distinguish and classify different geometric objects.
So why is orientability a problem here? Didn't we deal with that a while ago with those other theories you mentioned?
Well, the thing is, orientability isn't always guaranteed when we're dealing with open curves.
Okay.
Those boundary strata we talked about earlier can mess things up. They can disrupt our sense of direction, making it challenging to define consistent invariants.
It sounds like these boundaries are really causing a lot of headaches.
They can be.
So how did the authors address this issue?
They tackle this challenge head-on by making some specific choices and introducing a new tool called relative spin structures.
Relative spin structures. Okay, that sounds complicated.
It can be a little bit, yeah.
Can you give me a simple way to think about those? They sound like something out of theoretical physics.
In a way they are. Think of them as a way to ensure we have a consistent compass.
Okay.
Even when we're navigating these tricky multi-dimensional spaces with those pesky corners.
Right.
They provide a way to restore our sense of direction and make sure everything is properly oriented.
So they're like adding a gyroscope to our mathematical GPS.
Yeah.
Keeping us on track even when the terrain gets rough.
That's a great way to visualize it. And this leads us to one of the key results highlighted in the paper. Theorem B. This theorem describes the construction of these global Kuranishi charts for moduli spaces of open stable maps, specifically emphasizing how those relative spin structures come into play to guarantee orientability.
So this theorem essentially says we can create a consistent, reliable map for these open curves.
Yes.
Even with all their added complexities, thanks to these relative spin structures.
Exactly. It's a powerful result that lays the groundwork for defining invariants in this setting.
Wow, that's impressive.
Yeah.
I'm starting to see just how significant this paper is.
Yeah.
But before I move on, I just want to make sure I have this straight.
Okay.
We've got these open curves causing all sorts of trouble with corners and orientability.
Right.
The authors introduced these Kuranishi charts, which are like maps for these complex spaces. And then they bring in these relative spin structures to make sure our compass is working correctly, even in those tricky corners.
Exactly.
Did I get that right?
You nailed it.
Okay. Feeling more confident now. But I know there were other important results in the paper.
Yes.
Especially those theorems you mentioned earlier.
Right.
I'm ready to dive deeper into those.
Yeah.
But maybe we should take a short break here and come back refreshed for part 2 of our deep dive.
That sounds like a good plan.
Okay.
We've covered a lot of ground already, and those theorems deserve their own dedicated discussion.
Great.
All right.
Sounds good.
See you in a bit.
Okay.
So we were just discussing Theorem B, which was a real game changer because it showed us how to construct those global Kuranishi charts for open stable maps, even with all the complexities introduced by boundaries, but that's just the tip of the iceberg.
Right.
This paper has a lot more to offer.
I'm all ears. You mentioned a few other theorems.
Right.
And I'm eager to hear what they reveal about this new theory.
Okay.
What's next on our agenda?
Let's move on to Theorem C.
Okay.
Remember those troublesome corners we talked about?
Yeah.
Those boundary strata that make the moduli space so much harder to handle?
Yeah.
Well, Theorem C dives deep into how these global Kuranishi charts behave on those very strata.
Okay, so we're zooming in on those tricky spots on our map.
Yeah.
What insights does this theorem offer?
It tells us that when we restrict our Kuranishi chart to a boundary stratum,
Okay.
we can understand it as a fiber product of Kuranishi charts coming from simpler moduli spaces.
Okay.
It's like breaking down a complex puzzle into smaller, more manageable pieces.
So instead of trying to navigate the entire jungle at once,
Right.
we can focus on smaller clearings.
Exactly.
That seems like a much more practical approach.
And what's even more remarkable is that this theorem also sheds light on the orientation signs associated with clutching maps,
Okay.
which are the operations that glue these simpler moduli spaces back together.
Ah, the clutching maps. They're like the glue that holds our map together.
Yes.
But why are these orientation signs so important?
They're crucial for ensuring that our compass still works correctly when we piece everything back together.
Right.
Remember those relative spin structures we talked about?
Yeah.
Well, these orientation signs help us track how those spin structures behave as we move between different charts.
And so it's like making sure the arrows on our individual maps align correctly when we combine them.
A perfect analogy. And this understanding of orientation signs is particularly important when we're dealing with higher genus curves,
Okay.
with multiple boundary components.
Right.
Things get really complicated in those cases.
Yeah.
But Theorem C gives us the tools to handle that complexity.
This is starting to feel like we're building a whole new set of navigational tools
Right.
for exploring this uncharted territory.
Yeah.
It's amazing how much information is packed into these theorems.
It really is. And this detailed analysis of orientation signs in higher genus cases is one of the major contributions of this paper.
Right.
It's a crucial step towards defining those elusive, higher genus open Gromov-Witten invariants, which have been a real puzzle for mathematicians for a long time.
Speaking of Gromov-Witten invariants, you mentioned earlier that we've seen some progress on those, at least for genus zero curves.
Right.
Can you tell me more about that?
Absolutely. And that's where Theorem E comes in.
Okay.
It provides a way to define genus zero open Gromov-Witten invariants for a weakly unobstructed Lagrangian submanifold.
All right.
These invariants give us valuable information about the number and types of open curves that satisfy certain geometric conditions within our symplectic manifold.
Okay, so if I'm understanding this correctly, these invariants are like a census for these open curves.
Yeah.
They tell us how many there are and what they look like.
That's a good way to think about it. And this information can be incredibly useful for understanding the geometry of Lagrangian submanifolds
Right.
and their relationship to the larger symplectic manifold.
So it's like we're finally able to get a clear picture of this hidden world of open curves.
Yes.
But you mentioned that Theorem E only applies to genus zero curves.
Right.
What about higher genus curves?
Yeah.
Are those invariants still out of reach?
For now, yes. While this paper lays a strong foundation, extending these constructions to higher genus open Gromov-Witten invariants remains a challenge.
Okay.
The authors acknowledge that we need more sophisticated algebraic tools to extract meaningful invariants from those more complex moduli spaces.
So we've got the map and the compass, but we still need a more powerful magnifying glass to analyze the data.
Exactly. Developing those algebraic tools is an active area of research, and it's where the future of this theory lies.
Yeah.
But even with this limitation, the progress made in this paper is significant.
I'm starting to get a sense of that.
Yeah.
We've gone from having very limited tools for studying open curves to having a whole new framework for understanding them.
Right.
It's like we've gone from using crude hand-drawn maps to having satellite imagery in GPS.
I like that analogy. It really captures the magnitude of the shift in our understanding.
Yeah.
We've covered a lot of ground here.
We have.
TCFTs, moduli spaces, Kuranishi charts, orientability, those crucial theorems.
Right.
It's a lot to absorb.
It is. And I have to admit, my brain is starting to feel a bit overloaded.
Yeah, I understand.
I think I need a moment to process everything before we dive into the final part of our deep dive.
That sounds like a good idea.
Yeah.
It's important to take a step back and let these concepts sink in.
Right.
Why don't we recap the key takeaways from this paper so far?
Okay.
And then we can take a short break before tackling the last part.
That sounds like a great idea.
Okay.
I think a recap would be really helpful at this point.
Okay, let's quickly revisit the main points.
Right?
We started by exploring open-closed, topological conformal field theories,
Right.
or TCFTs for short,
Right.
which involve chains on moduli spaces of bordered curves acting on chain complexes.
Yeah.
We then discussed how these TCFTs can be understood through the lens of ASIC categories,
Right.
providing a way to organize and classify them.
Right. And that led us to the open-closed Deligne Mumford field theory,
Yes.
which brings together string topology and cobordism categories to create a unified framework for studying both open and closed curves.
Exactly. And then we got into the nitty-gritty of the paper,
Yeah.
exploring those powerful global Kuranishi charts for open stable maps.
Right.
These charts provide us with coordinate systems to navigate these complex moduli spaces,
Right.
even when dealing with those pesky corners introduced by boundary strata.
And let's not forget the crucial role of relative spin structures,
Yeah.
which ensure that our compass is always pointing in the right direction, even in those tricky corners.
Right. We highlighted Theorem B, which guarantees the orientability of these Kuranishi charts,
Yeah.
thanks to those relative spin structures.
Right.
Then we moved on to Theorem C, which explained how these charts behave on those boundary strata, breaking them down into simpler pieces that are easier to understand.
Right.
And of course, we can't forget Theorem E,
Right.
which gave us a way to define those elusive genus-zero open Gromov-Witten invariants, giving us a valuable tool for studying the geometry of Lagrangian submanifolds.
Exactly. It's been quite a journey so far.
It has.
And we've uncovered some fascinating insights into the world of open curves.
We have.
But remember, this is just the beginning.
Right.
There's still much more to explore, especially when it comes to those higher genus invariants.
Exactly.
I'm definitely sensing that. It feels like we've only scratched the surface of this vast and intricate landscape.
That's the beauty of mathematics, isn't it?
Yeah.
There's always more to discover, more connections, to uncover more mysteries to unravel.
Absolutely.
So,
Okay, I'm ready for a short breather.
okay.
Let's grab a cup of coffee and then come back refreshed to tackle the final part of this deep dive.
Sounds like a plan. I'm excited to see where this journey takes us next.
Okay, so I've been looking over this paper again, and one thing that really stuck with me was the discussion of the moduli space itself,
Okay.
especially how it relates to complex projective space.
Right.
There was this mention of a doubling map
Yeah.
and its connection to real structures. Can you kind of unpack that for me? What's going on there?
Sure. So the basic idea is to connect the moduli space of open stable maps,
Okay.
which are curves with boundaries,
Right.
to the corresponding moduli space of closed stable maps.
Okay.
And this connection is made through this construction called the doubling map.
So we're taking these open curves
Yes.
and closing them up somehow. How does that work?
Imagine you have an open curve,
Right.
like a line segment.
Okay.
The doubling map essentially takes two copies of this curve
Okay.
and glues them together along their boundaries,
Okay.
creating a closed curve like a circle.
By taking two halves of a world map
Exactly.
and stitching them together to make a globe.
Precisely. Now, this doubling map allows us to leverage
Okay.
existing knowledge about the moduli space of closed stable maps,
Right.
which is relatively well understood
Yeah.
compared to its open counterpart.
Okay.
But we need to be mindful of the real structure involved.
Real structure. Can you
Yeah.
explain what you mean by that?
Well, complex projective space, which is where our curves are living,
Okay.
has a natural real structure given by complex conjugation.
Okay.
Think of it as a reflection across a mirror.
Right.
The real projective subspace is precisely the set of points that are fixed by this reflection.
Okay.
They're their own mirror images.
So we're not just gluing any two open curves together.
Right.
We're specifically considering those that respect this real structure,
Yes.
making sure that the resulting closed curves also lie within complex projective space.
Exactly. This compatibility with the real structure is crucial for connecting our open setting to the well-established theory of closed Gromov-Witten invariants.
So it allows us to use what we already know
Yes.
about those closed invariants.
Exactly. It builds a bridge between these two seemingly different worlds.
No, I noticed that the paper also dives into some pretty technical details
It does.
about orientations and how they behave under this doubling map.
Right.
It mentions that the orientation on the moduli space of open stable maps needs to be compatible with the doubling map.
Yes.
Can you unpack that a bit? What's going on there?
So this compatibility of orientations is essential
Okay.
for making sure the invariants we define are consistent
Right.
and well-defined.
Okay.
We need to ensure that our compass still works correctly
Right.
after we've stitched our maps together using the doubling map.
So checking our sense of direction is still good,
Yes,
even after we've glued things together.
precisely. The paper goes through a detailed analysis
Okay.
of the tangent spaces involved and how the real structure acts on them
Right.
to show that under certain conditions, the moduli space of open stable maps can be given a natural orientation
Okay.
that's compatible with the doubling map.
So we're really carefully analyzing the geometry to make sure everything lines up,
Right.
even after this gluing process.
Exactly.
Well, it's like a delicate balancing act.
It is. But this meticulous attention to detail
Right.
is what gives this theory its rigor and power.
I see.
By carefully analyzing these geometric and algebraic structures, the authors have created a framework that opens up a whole new way of understanding open curves and their invariants.
This has been quite a journey. We've gone from those initial concepts of TCFTs and A categories to these intricate moduli spaces
Right.
and their connection to complex projective space.
It's been a lot.
Learned about these powerful theorems. Explore the challenges that still lie ahead.
Yeah.
It's been challenging,
Definitely.
but incredibly rewarding.
It has been a really interesting deep dive.
To our listeners, if you've made it this far,
Yeah.
you've just completed a deep dive into one of the most cutting-edge areas of mathematics.
Absolutely.
We hope this journey has sparked your curiosity, inspired you to explore the world of open curves and their invariants further.
It's a fascinating area.
As always, the original paper is a treasure trove of details and insights.
Definitely worth checking out.
And we encourage you to dive in and discover its riches for yourselves.
I agree.
Until next time,
Yeah.
keep exploring,
Keep questioning.
keep pushing the boundaries of knowledge.
And who knows?
Maybe one day you'll be the ones making the next groundbreaking discovery
Absolutely.
in this fascinating field. All right, so today we're going to be diving into some pretty heavy mathematical waters. We're tackling open-closed Deligne Mumford field theory associated with a Lagrangian submanifold.
Yeah, this is really where symplectic geometry and algebraic geometry and even string theory all kind of come together.
Okay, so to set the stage for our listeners who might not be, completely immersed in this world, could you just give us a quick recap of what Lagrangian flower theory is and the Fukaya category? They're kind of the foundation for what we're talking about, right?
Right, exactly. So Lagrangian flower theory, studies the intersections of Lagrangian submanifolds inside a symplectic manifold, and it uses these intersections to build this chain complex. And the homology of that chain complex gives you these invariants called flower homology groups.
Right.
And then the Fukaya category kind of takes that a step further. It's basically a category where the objects are Lagrangian submanifolds. And the morphisms are these floor chain complexes. So it gives you this kind of algebraic framework for studying these Lagrangian intersections.
So we're dealing with these intricate algebraic structures that are built on, the geometry of these Lagrangian submanifolds. And this paper, is trying to extend these ideas to open-closed strings.
Yeah.
Is that right?
That's right. The challenge is that when you go from closed curves to these bordered curves, things get a lot more complicated. The moduli spaces of these bordered curves can be non-orientable, and they have these codimension 1 strata that make constructing invariants a lot trickier.
I can already feel the headaches coming on. But this paper seems to make some real progress, even for higher genus curves.
They do. And one of the key ideas they introduce is this framework of open-closed topological conformal field theory, or TCFT for short. And they use that as a way to kind of understand the algebraic structure of these moduli spaces, even in these higher genus scenarios.
Okay, so TCFT, let's unpack that a little bit.
Yeah.
What's the basic idea? That sounds pretty intimidating.
Yeah, so, the basic idea is that it involves these chains on moduli spaces of bordered Riemann surfaces. And these chains kind of act on a pair of chain complexes. Each complex is kind of associated to boundary punctures or interior punctures on these surfaces. So, you're basically encoding the interactions of open and closed strings within this algebraic framework.
So I'm picturing, we've got these Riemann surfaces with boundaries, and those are representing the world sheet of the strings.
Right.
And we have these punctures on those surfaces, which were representing points where strings can either begin or end.
Exactly.
And the TCFT is giving us a way to capture like the algebraic essence of how those strings are interacting.
Exactly. Yeah. And one of the really neat things is that if you kind of restrict this TCFT to the operative disks with boundary punctures, you get what's called an A infinity category.
Okay.
And surprisingly, you can actually also go the other way. If you start with an A infinity category, you can construct a TCFT.
So there's this kind of duality between TCFTs and A infinity category.
Yeah, there is.
Okay, so we're already deep in the world of abstract algebra here.
Yeah.
But how does this all relate to open-closed Deligne Mumford field theory? Because that's really the focus of the paper, right?
Yeah, that's right. So open-closed Deligne Mumford field theory is a particular type of TCFT. So you can think of it as a symmetric monoidal functor from a certain category of moduli spaces of these bordered Riemann surfaces to the category of chain complexes.
Okay, so we have this functor, and it's mapping geometric objects, these moduli spaces, to algebraic objects, these chain complexes.
Right, right.
But what are the key ingredients of this functor? Like, what makes it an open-closed Deligne Mumford field theory?
Okay, so there's kind of three main components. So first you have the closed state, which you can think of as the ground state of the closed string sector. Then you have chain contexts that are associated to these D-branes, which are basically submanifolds where open strings can end.
Right. So those are kind of like the endpoints are stuck to the D-branes.
Exactly. Yeah. And then the third component is a set of linear maps that go from chains on these moduli spaces to morphisms between the chain complexes. So they kind of encode how the geometry of the moduli spaces dictates the interactions between open and closed strings.
So this functor is really capturing the essence of open-closed string theory in this algebraic framework.
Right.
And this paper is aiming to construct a specific open-closed Deligne Mumford field theory using Gromov-Witten theory. Is that right?
That's exactly right. Yeah.
Okay. So there's a lot of heavy lifting involved in this, I'm sure. So where do they even begin? Like, what's the first hurdle they need to overcome?
Well, the first challenge is really to understand the structure of these moduli spaces of bordered curves.
Okay.
And the key tool that they use for this is the concept of a global Kuranishi chart.
Okay. So I've heard of Kuranishi structures before, but remind me, what are they all about?
Okay, so basically a Kuranishi structure on a moduli space gives you a way to kind of describe the space locally as the zero set of a certain map between manifolds.
Right.
So it's a way to give the moduli space some kind of smooth structure, even though it's not technically a smooth manifold itself. And a global Kuranishi chart is basically an extension of that idea. It gives you a way to describe a larger portion of the moduli space in a consistent way.
Okay, so we're trying to give these moduli spaces some semblance of smoothness,
right,
so we can work with them.
Yeah, that's exactly right. And the tricky part is that in the case of open stable maps, these moduli spaces kind of develop corners and boundary strata, which makes the construction of these global Kuranishi charts more delicate.
Right, right. Yeah, it's starting to sound complicated. So they focus specifically on projective space and its real locus when they're building these global Kuranishi charts.
Yeah, they do. And they show that in this case, you can actually construct these global Kuranishi charts that are smooth and orientable and compatible with the action of certain Lie groups.
Okay, so we've got these global Kuranishi charts. They give us a way to, get a grip on the structure of these moduli spaces.
Right.
But then the next big hurdle seems to be figuring out these orientation signs.
Yeah.
Why are they so important in this whole construction?
So orientation signs are really important because they're what ensure that that the field theory that we're constructing is well defined.
Okay.
So you see a lot of the key operations and constructions involve integration over these moduli spaces. And to integrate over a space, you need to have a way to orient the integration domain.
Right.
So if the moduli spaces are non-orientable, meaning you can't assign a consistent orientation, these integrals can become ill-defined, and the whole theory can kind of fall apart.
So it's like we're trying to build a house, and these orientation signs are telling us whether we're putting the bricks in the right direction.
Exactly. That's a great analogy.
If we get the signs wrong, the whole structure could collapse.
Yeah. Yeah. And, this is, I think, potentially the first time these orientation signs have been worked out for open stable maps in higher genus.
Oh, wow.
So, they build on some recent work by Chen and Zinger, who developed this powerful framework for handling orientations in Gromov-Witten theory. And the key concepts they use are relative spin structures and background classes.
Okay.
So, roughly speaking, a relative spin structure gives you a way to assign orientations to loops in the tangent bundle of your moduli spaces.
Okay.
And a background class is basically a cohomology class that helps you determine whether or not you can even define such a relative spin structure.
So can you give us an example of like a specific situation where these orientation signs become really important?
Yeah, so a crucial place where they come in is when you're gluing together different pieces of these moduli spaces.
Okay.
So these gluing operations are essential for understanding how the moduli spaces change as you vary the parameters of the problem.
Right. Like if we're changing the complex structure on our Riemann surfaces or the symplectic form on our target manifold.
Exactly, yeah.
Okay.
And when you glue these pieces together, you need to make sure that the orientations kind of match up correctly. Otherwise, you can introduce kind of spurious signs that will mess up your calculations. So the paper very carefully analyzes these gluing operations and shows how to determine the appropriate orientation signs based on these relative spin structures and background classes.
So they're really like meticulously going through every nook and cranny of these moduli spaces, making sure every sign is accounted for.
Yeah, they really are. And, it's not just about getting the signs right. It's about understanding why those signs are what they are.
Right.
So, uncovering the deeper geometric and topological reasons behind those choices.
It's like they're deciphering some kind of secret code hidden within the geometry of these moduli spaces.
Exactly. That's a great way to put it. And they don't just stop at the gluing operations. They also look at the orientation signs for various boundary strata, and they highlight the role of these things called intrinsic and limiting orientations of Cauchy-Riemann operators in these calculations.
Okay, so they're leaving no stone unturned in their quest for a complete understanding of these orientations.
Yeah, they are.
Now, before we get too lost in the labyrinth of signs and orientations, can we take a step back and talk about these Tom forms and Tom systems that they introduce?
Correct.
What role do they play in this whole construction?
Right. So they play a crucial role in defining those cooperations that we mentioned earlier.
Okay.
So remember that the cooperations are what we use to actually construct the open-closed Deligne Mumford field theory.
Right. They're the ones that give us those invariants that capture the essence of the theory.
Exactly. Yeah. So to define these cooperations, we need to use these things called Tom forms.
Okay.
And basically a Tom form is, it's a differential form that represents a certain cohomology class called the Tom class, which is associated to a vector bundle.
Okay, so we have these vector bundles floating around, and the Tom forms are like their cohomology representatives.
Exactly.
But how do they connect to the cooperations?
Right. So the key idea is that we can integrate these Tom forms over certain cycles in our moduli spaces. And these cycles kind of represent the contributions of different types of curves to our invariants.
So we're using these Tom forms to kind of weigh the contributions of different curves.
Exactly. Yeah.
Yeah.
That's a good way to put it. And a Tom system is basically a collection of compatible Tom forms that work together to define these cooperations across all the relevant moduli spaces.
Okay, compatible in what sense?
So they need to satisfy certain conditions that are related to the forgetful maps between these moduli spaces.
Okay.
So remember that forgetful map basically takes a moduli space with, say, n marked points and forgets one of those points.
Right. So we're erasing one of the points where a string could end.
Exactly. And so the Tom forms in our system need to behave nicely under these forgetful maps. So the paper carefully constructs these Tom systems and proves that they have the right compatibility properties.
So it sounds like they're setting up this really delicate system of like weights and measures, carefully calibrated to capture the intricate interplay between these open and closed strings.
That's a great way to think about it. It's a really beautiful blend of geometry and algebra and analysis all working together to build this powerful theoretical framework.
Yeah, I'm starting to get a sense of just how much work has gone into building this theory.
Oh, yeah.
It's like we're assembling this this complex piece of machinery, and every nut and bolt needs to be, precisely in place.
Yeah, it really is. And then, the paper goes into even more kind of intricate details like the inductive construction of these TOM systems and the use of these things called strongly unobstructed auxiliary data and the extension of TOM forms from boundary and divisor strata.
Wow.
It's really a testament to the rigor and precision that's required in this kind of mathematics.
Well, I think we're just scratching the surface here of the technical depths of this paper.
Yeah, we are.
But it's already incredibly fascinating, even at this level. It's amazing to see how these abstract mathematical tools can be used to understand concepts from theoretical physics, like string theory.
Yeah, absolutely. And it's a reminder that that even in very advanced mathematics, there's always more to learn, more connections to discover, more mysteries to unravel.
Okay, well, I think we've covered a lot of ground in this first part of our deep dive. We've laid the groundwork, explored the the motivation behind the theory and the challenges involved, and some of the key tools they use to construct this open-closed Deligne Mumford field theory.
Yeah, I think we've set the stage for a deeper exploration of the theory's details and its applications.
And on that note, I think we should take a short pause to let all this information sink in. We'll be back soon to continue our journey into the fascinating world of open-closed Deligne Mumford field theory.
Okay.
And so we've laid the groundwork, explored those global Kuranishi charts and the importance of orientation signs. I'm ready to dive deeper into the construction of the actual open-closed Deligne Mumford field theory itself.
Excellent. It's time to put all the pieces together and see how this intricate mathematical machinery actually works.
Okay, so if I remember correctly, they use Gromov-Witten theory as the engine for this construction.
Yeah.
Can you remind us how that fits into the picture?
Certainly. Gromov-Witten theory provides a powerful framework for defining invariants by counting J-holomorphic curves, which are maps from Riemann surfaces into our symplectic manifold that satisfy a specific differential equation.
Right. Those J-holomorphic curves are kind of like the fundamental building blocks in this whole story.
Exactly. And the paper meticulously outlines how to adapt this framework to construct an open-closed Deligne Mumford field theory. They start by defining a symmetric monoidal functor. They denote this functor as a UNO.
So this functor is the star of the show. It's going to connect the geometry of these moduli spaces to the algebra of chain complexes.
You got it. This functor maps from a category of moduli spaces of bordered Riemann surfaces to a category of chain complexes over a specific ring. And remember, the ring we're working with here is the Novikov ring, denoted by UNO. This ring is specially designed to handle the subtleties of counting curves in this setting.
Right. The Novikov ring helps us keep track of those curve counts in a way that respects the homology classes of the curves. It's a bit more sophisticated than just counting with integers.
Exactly. Now, this functor has a few key ingredients. They are the closed state, chain complexes associated with D-branes, and linear maps associated with chains on moduli spaces.
Okay, let's break those down one by one. What exactly is this closed state?
The closed state, often denoted as V, represents the closed string sector of the theory. Think of it as the space of states for closed strings propagating in our symplectic manifold. It captures the information about the closed string background.
Okay, so V is like the closed string universe in our setup. Now, what about those chain complexes associated with D-branes?
D-branes in string theory are these hypersurfaces where open strings can end. In this mathematical context, we associate each D-brane denoted as L with a chain complex denoted as WL, L1, L2.
So each D-brane has its own little chain complex attached to it.
Exactly. And this complex WL1, L2 captures the interactions between open strings starting on a D-brane L1 and ending on another D-brane L2.
So we're encoding the open string dynamics in these chain complexes. It's like each D-brane is a stage where open strings can interact. What about those linear maps associated with chains on moduli spaces? Where do they fit into the picture?
These linear maps, denoted as VAS, are the heart of the functor. They connect the closed string sector, represented by V, to the open string sector, represented by those chain complexes associated with D-branes.
So they're bridging the gap between the closed and open string worlds.
Precisely. Each chain within a moduli space is associated with a specific linear map. This map describes how closed strings interact with and potentially create open strings on D-branes. It captures the dynamics of how those strings can transition between those two sectors.
It's like these linear maps are the rules of the game, dictating how strings can move between those closed and open string stages.
That's a great way to visualize it. And these maps are not just any old maps. They're carefully chosen to be chain maps, meaning they respect the differential structure of those chain complexes.
Right, those differentials are encoding the topological information about the strings and their interactions.
Exactly. So these chain maps ensure that the functor preserves the relationships and structures from both the geometric and algebraic realms. It's a beautiful interplay between those two worlds.
Okay, so we have all these components in place, the closed state, the D-brane chain complexes, and those linear maps connecting them. But how do we actually extract information from this functor? How do we get those invariants to tell us something meaningful about the underlying geometry?
That's where those cooperations come into play. Remember, we briefly mentioned them earlier.
Right, there were these mysterious operations that somehow capture the essence of the theory.
Exactly. The cooperations are crucial because they provide a way to perform computations within this framework. They're defined using what are called admissible simplices, which are essentially maps from a standard simplex, which you can think of as a higher dimensional triangle, into those moduli spaces of curves.
So we're mapping these abstract geometric shapes, these simplices, into those spaces representing all possible curves.
Precisely. And each admissible simplex is associated with a particular cooperation. To define this cooperation, we use the Tom forms that we discussed previously.
Right, those Tom forms were those cohomology representatives of the vector bundles?
Exactly. We integrate a specific Tom form over the fibers of a certain forgetful map between moduli spaces. This integration process, using the Tom form as a weight, yields the cooperation associated with that simplex.
Okay, so we're taking those Tom forms, integrating them over certain parts of those moduli spaces, and out pop these corporations. It's like squeezing the geometric information out of those spaces.
You got it. And the paper proves that these cooperations satisfy certain relations and axioms that make them incredibly powerful tools for computation. They're the key to unlocking the secrets of this open-closed Deligne Mumford field theory.
It sounds like those cooperations are like the keys to a treasure chest full of geometric insights.
That's a great analogy, and what's remarkable is that as the paper rigorously proves, this whole intricate construction actually satisfies all the axioms of an open-closed Deligne Mumford field theory.
So we've built this complex mathematical machine, and it actually works. It does what it's supposed to do.
Exactly. And it's not just an abstract exercise. This theory has real implications for our understanding of symplectic geometry and string theory.
Okay, so we've built this beautiful theory, but how do we actually use it? What can we do with this open-closed Deligne Mumford field theory once it's all set up?
That's the exciting part. One of the key applications is the construction of open Gromov-Witten invariants, which are numerical invariants that count open curves, meaning curves with boundaries that satisfy certain conditions within our symplectic manifold with a chosen Lagrangian submanifold.
So we're using this theory to count those open curves in a sophisticated way. How do these open Gromov-Witten invariants work?
The idea is to leverage those cooperations we defined earlier. By carefully analyzing how those cooperations compose and relate to each other, we can extract these numerical invariants.
It's like those cooperations are the tools we use to dissect the geometry and extract those hidden numerical gems, those invariants.
Exactly. And these invariants can tell us a lot about the underlying geometry. They can help us distinguish different symplectic manifolds and Lagrangian submanifolds. It's like giving each of those spaces a unique fingerprint.
So we're taking this abstract algebraic machinery and we're using it to uncover hidden patterns in geometry. It's pretty amazing.
It is. And it's a reminder that abstract mathematics, while challenging, can lead to profound insights into the nature of the world around us.
Now, the paper mentions that constructing these open Gromov-Witten invariants is especially challenging in higher genus scenarios.
That's right. As the genus of the curves increases, the complexity of those moduli spaces grows significantly, making the calculations and the interpretation of those invariants much harder.
Right, they discuss those special cases in the introduction where progress has been made, like when the Lagrangian submanifold has certain symmetries. But a general construction for all higher genus cases is still an open problem.
It is. It's an active area of research pushing the boundaries of our understanding of those moduli spaces and those intricate invariants. The paper highlights a few recent results, like those by Ekholm and Shende, that define skein-valued, open Gromov-Witten invariants in all genera for a special type of three-dimensional manifold called a Calabi-Yau threefold.
So even though there's no complete solution yet, there's definitely progress being made.
Absolutely. And it's exciting to see how mathematicians are developing new techniques and approaches to tackle these challenges.
Now, before we move on, you mentioned something earlier about a connection between open-closed Deligne Mumford field theory and string topology. That caught my attention. Can you tell us a bit more about that?
Certainly. String topology is a fascinating area of mathematics that studies the algebraic structure of the space of loops in a manifold. It turns out that there are deep and surprising connections between string topology and open-closed string theory.
So this abstract mathematical theory we've been exploring actually has ties to the physics of strings. That's pretty wild.
It is. The paper briefly mentions a 2009 paper by Blumberg, Cohen, and Telemann that explores how open-closed field theories, like the one we've been discussing, can be used to understand certain algebraic structures arising in string topology. They show that those structures can be naturally interpreted in the language of open-closed field theories.
It's fascinating how these different areas of mathematics, each with its own set of tools and perspectives, can converge and illuminate each other in such unexpected ways.
It speaks to the underlying unity and interconnectedness of mathematics, and these connections often lead to new breakthroughs and insights.
Okay, now that we've explored the construction of this open-closed Deligne Mumford field theory and some of its applications, I think it's time to tackle one of the most technically challenging aspects: the orientability of those moduli spaces.
Yes, that's a crucial point. As we touched upon earlier, those orientation signs are absolutely essential for ensuring that the entire theory is well-defined and that our calculations make sense.
Right, it's like making sure we're not building our mathematical house on a foundation of shifting sand.
Exactly. If those moduli spaces aren't orientable, meaning we can't consistently assign orientations to them, then the whole theory can fall apart. Many of the key results and constructions rely on having well-defined orientations.
Okay, so we need to dive into this world of orientability and make sure everything is properly oriented. What's the general approach they take in the paper?
They rely on the framework of relative spin structures, which are a way of adapting the concept of spin structures from differential geometry to the realm of symplectic geometry. A spin structure, roughly speaking, gives us a consistent way to assign signs to loops in the tangent bundle of a manifold. A relative spin structure extends this idea to pairs of spaces like our symplectic manifold and the Lagrangian submanifold we've chosen.
So a relative spin structure is like a set of instructions for assigning orientations in a way that respects the relationship between those two spaces.
That's a good way to think about it. Now, to actually define these relative spin structures, they use a background class, which is a specific cohomology class associated with the Lagrangian submanifold.
So the background class, denoted as ρs, is like a key that unlocked the ability to define those relative spin structures.
Precisely. The paper delves into the various conditions and relationships between this background class and the topology of the Lagrangian submanifold to establish when we can define those structures, and therefore when our moduli spaces are orientable.
So it's all about understanding the interplay between the topology of that Lagrangian submanifold and this mysterious background class.
Exactly. And they explore specific cases to illustrate how different scenarios affect orientability. For example, they analyze cases where the background class vanishes or satisfies certain properties. Each case sheds light on the subtle relationship between those topological ingredients and the orientability of those moduli spaces.
It's like they're piecing together a complex jigsaw puzzle, where each piece represents a different condition or property that affects the overall picture.
That's a great analogy. And it's not just about finding the right pieces, it's about understanding how they fit together, what patterns emerge, and what those patterns tell us about the bigger picture.
It's like we're decoding a hidden message embedded within the geometry of these spaces.
I love that. It's a poetic way to capture the essence of what's going on here. The paper doesn't just stop at the general framework, it dives into specific cases of boundary strata and explains how to determine the appropriate orientation signs for each.
Right, because those boundary strata are where things can get really tricky.
They are. And the paper meticulously analyzes how the orientation lines behave near those boundary strata. They use tools like intrinsic and limiting orientations of Cauchy-Riemann operators to carefully work out the appropriate signs in each case.
Sounds like they're meticulously combing through every nook and cranny of those moduli spaces,
Hmm.
making sure every sign is accounted for.
They are, and they highlight how the presence of boundary nodes adds extra complexity because they introduce additional degrees of freedom and affect how those orientation lines behave.
So those boundary nodes are like little wrinkles in the fabric of those moduli spaces that we need to iron out carefully.
That's a great visualization. And to handle those wrinkles, they carefully analyze the gluing maps that connect different parts of the moduli spaces near those boundary nodes.
Right, those gluing maps are essential for understanding how those moduli spaces fit together.
Exactly. They meticulously dissect the behavior of those gluing maps and their derivatives to determine how they affect those orientation lines. They use some heavy-duty tools from functional analysis like weighted Sobolev spaces and Fredholm theory to control the regularity and properties of those maps and their linearizations.
So they're bringing in some serious mathematical firepower to tame those unruly gluing maps and their impact on orientations.
They are, and they pay close attention to the different types of boundary nodes as different configurations can lead to different orientation behaviors.
So each case needs to be handled with care and precision. It's like they're diffusing a series of mathematical bombs, each with its own unique set of wires to untangle.
That's a vivid way to put it, and it highlights the incredible amount of detail and rigor required in this kind of work.
Okay. I think we've done a pretty thorough job of exploring those orientation issues.
Mhm.
Definitely a challenging aspect of this theory, but it's clear that they've gone to great lengths to ensure everything is well-defined and consistent.
They have, and it's testament to the power of abstract mathematical tools in handling such subtle and intricate details.
Well, we've covered a lot of ground in this second part of our deep dive. We've explored the construction of the open-closed Deligne Mumford field theory, delved into the intricacies of those cooperations, and tackled the challenges of orientability.
We've really started to see how this theory takes shape and how it connects to other areas of mathematics like string topology.
And in the final part of our deep dive, we'll wrap things up by discussing the broader implications and potential applications of this theory.
Yes, there's still much to explore. We'll delve into how this theory can be used to understand the geometry of symplectic manifolds and how it opens up new avenues of research in both mathematics and physics.
Welcome back to our deep dive. We've been exploring open-closed Deligne Mumford field theory.
We've covered a lot of ground, those global Kuranishi charts, those orientation signs. It's pretty intricate stuff.
It is, but I'm really eager to dig into the implications and applications now we've kind of laid that foundation.
Yeah, it's amazing how this seemingly abstract theory can unlock insights into symplectic geometry, even connect to string theory.
Speaking of string theory, you mentioned open Gromov-Witten invariants earlier. Can you expand on how this theory helps us define and understand those?
Of course. So open Gromov-Witten invariants, they give us a way to count open curves, the ones with boundaries. These curves have to satisfy specific conditions in our symplectic manifold, which also has a Lagrangian submanifold.
Right. It's like we're quantifying these open curves, which gives us a deeper understanding of the geometric structures.
Exactly. And the beauty of open-closed Deligne Mumford field theory is that it gives us this rigorous framework for defining and actually computing these invariants.
Can you walk us through how that works? How do we go from this abstract theory to, actual numerical invariants?
Well, the key is in those cooperations we talked about. They hold a lot of information about the moduli spaces of curves and how they relate to each other.
Right. They're like our tools for extracting those geometric insights.
Precisely. By carefully analyzing how these cooperations work, how they compose, how they interact, we can derive these numerical invariants.
So it's like we're playing with these cooperations like puzzle pieces, and the solution is the invariant we're looking for.
A very good analogy.
Now, the paper mentions that this constructing these open Gromov-Witten invariants gets really tough in higher genus situations.
It does. The complexity explodes as the genus increases. It becomes much harder to grasp the structure of those moduli spaces and do the computations.
So higher genus means more complicated moduli spaces and harder to find invariants.
That's the gist of it. The paper points out some special cases where progress has been made, like when the Lagrangian submanifold has certain symmetries. But a general method for all higher genus cases is still out there, waiting to be discovered.
Right, those specific cases give us some clues, but the bigger picture is still kind of blurry.
It is an active area of research. Mathematicians are working on it, pushing the boundaries of what we know about these moduli spaces and these complex invariants. For instance, there's work by Ekholm and Schende. They define what are called skein-valued open Gromov-Witten invariants. This works for all genera, but in a specific type of three-manifold, a Calabi-Yau threefold.
So progress is being made even if we don't have all the answers yet.
Absolutely. And it's exciting to see how mathematicians come up with these new techniques and approaches to tackle these problems.
But it's not just about the technical challenges. These invariants have deeper meaning for understanding symplectic geometry, right?
They do. They give us new tools to tell apart different symplectic manifolds and different Lagrangian submanifolds.
Like fingerprints, revealing the unique qualities of those geometric objects.
Exactly. And they might even illuminate relationships between different geometric structures, leading to new connections and discoveries.
The potential applications are really intriguing, both within symplectic geometry and beyond.
Yeah, it's a field with a lot of unexplored territory. Lots to discover.
Okay, before we wrap up completely, let's go back to something that really fascinated me. The connection between this theory and string topology.
Right. It's a great example of how different areas of math can come together in surprising ways.
Remind us again what string topology is about and how it links to this theory.
String topology basically studies the algebra behind the space of loops in a manifold. Imagine all the possible loops you can draw in a space, and we turn that whole collection into a mathematical object with its own rules and relationships.
So we shift our focus from points to loops.
Yeah, and the amazing thing is that the algebraic structures you find in string topology have deep connections to open-closed string theory and physics.
So we started with abstract loops on manifolds, and now we're talking about the physics of strings.
It is a remarkable connection. The paper even mentions a paper by Blumberg, Cohen, and Telemann. They showed that you can understand certain algebraic operations in string topology using these open-closed field theories.
It's mind-blowing how different parts of math, each with its own tools and way of thinking, can come together and shed light on each other.
It really speaks to a fundamental unity in mathematics, and these unexpected connections often lead to major breakthroughs.
Well, as we come to the end of our deep dive, I feel both, a sense of awe and also inspiration. It's been a challenging journey, but the insights have been so rewarding.
It's been a pleasure exploring this with you. I hope it's sparked a curiosity to learn even more about open-closed Deligne Mumford field theory.
A big thank you to you, our expert. And to our listeners, thanks for joining us on this adventure.
The journey of mathematical discovery is never-ending. There's always something new to learn, new connections to make, new mysteries to solve.
So keep those questions coming, keep pushing the boundaries, and who knows what mathematical treasures you'll find.
Until next time, happy exploring!
Welcome to our deep dive today. We're going to be looking at open-closed Deligne Mumford field theory associated with a Lagrangian submanifold.
Right.
It's a pretty dense topic.
It is.
But I think we can unpack the key ideas here.
Absolutely. Yeah. The paper presents, I think, a really novel construction
that
addresses some long-standing challenges in defining these enumerative invariants, particularly in the open setting.
Right. We've seen some success with closed curves and closed symplectic manifolds. But when we introduce boundaries and the Lagrangian boundary conditions, things get a lot more
much more complex.
Yeah.
The non-orientability of moduli spaces and the presence of codimension 1 strata have been major roadblocks.
Right.
Researchers like Welschinger, Liu, and Georgieva have made progress in specific scenarios.
Yeah.
But a general framework has been elusive.
And that's where this paper comes in.
Exactly.
They're proposing kind of a new approach. And it seems like they're drawing some inspiration from Costello's work on open-closed topological conformal field theory.
Exactly.
Okay.
Their construction relies on global Kuranishi charts and focuses on a specific case involving projective spaces and their real submanifolds.
Right.
And it's a clever approach that offers a way to navigate the complexities of these open Gromov-Witten invariants.
Okay, so let's start with those. What exactly are open Gromov-Witten invariants, and why are they so crucial in this whole story?
Well, imagine you have a symplectic manifold and a Lagrangian submanifold within it. Open Gromov-Witten invariants, in essence, count the number of ways you can map a surface with boundary into the space, ensuring the boundary lands on the Lagrangian submanifold.
So it's like counting the number of ways you could drape a sheet over a sculpture, making sure the edges always touch a specific part of the sculpture.
That's a good analogy. Yeah. The problem is defining these invariants rigorously, especially for higher genus surfaces, has been incredibly challenging.
So this paper is tackling a pretty tough problem then. And I'm guessing understanding the moduli spaces of these maps is...
Absolutely.
Okay.
The paper dives deep into the algebraic structure of these moduli spaces,
Right.
specifically leveraging the power of global Kuranishi charts.
Right. Those charts were mentioned in the introduction.
Yeah.
Can we break down what they are and why they're so important here?
Certainly. Global Kuranishi charts provide a way to smooth out the structure of moduli spaces, which can be quite singular and difficult to work with directly.
Right.
Theorem B in the paper, for example, shows how they can give a smooth, orientable manifold with corners structured to the moduli space of open stable maps into projective space with boundary in the real projective space.
So they're like a set of coordinates that give us a better grip on these complicated spaces.
And what's interesting is that these charts have corners, and their boundary strata are fiber products of other moduli spaces. This reflects the fact that we're dealing with open maps, and we need to account for the various ways these maps can degenerate.
It makes sense. So these corners are like bookmarks indicating different types of degenerations.
Exactly.
Okay.
And understanding how these charts behave when restricted to these boundary strata is crucial for defining our open Gromov-Witten invariants.
Okay, so global Kuranishi charts provide a really powerful framework for analyzing these moduli spaces. But the paper also delves into some really intricate details about orientation signs and clutching maps. Why are these concepts so important?
Orientation is crucial because it ensures consistency as we move around the moduli space.
Okay.
Think of it like choosing a consistent way to define clockwise and counterclockwise on a surface.
Right.
Clutching maps, on the other hand, are the operations we use to glue surfaces together along their boundaries.
So if we don't pay attention to these orientation signs, our glued surfaces might end up with inconsistent directions, and the whole theory could fall apart.
That's the danger.
Okay.
Theorem C in the paper provides a precise understanding of how these global Kuranishi charts behave when restricted to boundary strata, including how the orientations transform under clutching maps.
That sounds incredibly important. It's like having a set of rules for ensuring that our gluing operations don't create any mathematical paradoxes.
And this paper is noteworthy because it's the first to comprehensively work out these orientation signs for moduli spaces of open stable curves, particularly in higher genus.
Okay, that's pretty significant. So we've got these global Kuranishi charts that provide a way to navigate these moduli spaces. And we're meticulously tracking orientation to make sure our gluing operations are consistent. But how does all of this lead to the actual definition of open Gromov-Witten invariants?
Well, that's where Theorem E comes into play. It asserts the existence of genus 0 open Gromov-Witten invariants associated with what are called weakly unobstructed closed Lagrangians.
Weakly unobstructed closed Lagrangians. Well, that sounds like a mouthful.
Of course.
Can you break that down for us?
Lagrangian refers to the special type of submanifold we're working with. Closed means that this submanifold is compact, like a sphere, rather than an infinite plane.
Right.
And weakly unobstructed is a technical condition that ensures the moduli spaces are well behaved and allow us to define invariants.
So under certain conditions, we can actually count these open curves and get meaningful invariants. That's a big step forward.
Absolutely. Okay. And these invariants have some remarkable properties. They remain unchanged even if we deform the symplectic structure or perform specific geometric transformations called Hamiltonian isotopies.
So no matter how we wiggle the space around, these invariants stay put. That's really cool.
Exactly.
It seems like a testament to the robustness of the theory.
It is.
Now, the paper also goes into great detail about constructing these global Kuranishi charts for open stable maps, including specific choices and conditions required. Could you elaborate on the main points of this construction?
Certainly. The construction involves choosing an auxiliary datum, which consists of a connection, a polarization, a covering, and other parameters. This datum helps in building a pre-thickening, which captures the deformations of both the stable maps and the domain curves. The authors then meticulously construct the global Kuranishi chart using these ingredients.
It sounds like a delicate process with a lot of moving parts. What are some of the key challenges or subtleties involved in this construction?
One of the key challenges is ensuring that the constructed global Kuranishi chart is compatible with the chosen auxiliary datum.
Right.
The paper meticulously lays out the conditions that need to be satisfied for this compatibility to hold.
Right.
Another challenge is dealing with the boundary strata of the moduli space, which arise from the degenerations of the open stable maps.
So it's not just about constructing the chart itself, but also ensuring that it plays nicely with all these other structures and behaves well near the boundaries.
Exactly. It's a delicate balancing act that requires a deep understanding of the underlying geometry and careful attention to detail.
Right.
The paper does a fantastic job of walking the reader through this intricate process step by step.
That's impressive. Now, once we have these charts, the paper delves into the concept of oriented equivalence between them. Can you explain what this equivalence means and why it's so important?
Oriented equivalence essentially means that two global Kuranishi charts are the same from the perspective of our theory, even if they might look different superficially.
Right.
It's like saying they're different maps at the same territory, just drawn from different perspectives.
So it's about abstracting away from the specific details of individual charts and focusing on the essential geometric structure they represent.
Lemmas 2.37 and 2.38 in the paper play a key role in establishing this equivalence.
Yeah.
They provide a rigorous way to compare different charts and determine when they capture the same underlying structure.
That makes sense. This equivalence seems crucial for ensuring our invariants are well-defined, regardless of which chart we choose to work with.
Precisely. It gives us a powerful tool to navigate the complexities of these moduli spaces and make sure our constructions are robust and independent of arbitrary choices.
Okay, so we have these global Kuranishi charts, and we have a way to tell when two of them are essentially the same. But the paper also discusses the classification of boundary strata based on clutching maps and collapse maps. What's the significance of these maps?
These maps describe the different ways surfaces can degenerate, which directly relate to the boundary structure of our moduli spaces.
Okay.
Understanding their properties is key to piecing together the complete picture of how these spaces behave.
It seems like we're meticulously analyzing all the possible ways these surfaces can break down or glue together to ensure that our theory captures all the nuances of these processes.
And as you might expect, the authors are very careful about keeping track of orientation signs throughout these operations.
Right.
They lay out specific assumptions and conventions for ordering boundary-marked points and boundary components, ensuring consistency across the board.
It sounds like we're establishing a strict grammar for these geometric operations to avoid any ambiguities or contradictions.
The paper even goes into determining the orientation signs for the lifts of clutching maps to morphisms between global Kuranishi charts.
Right.
This level of detail ensures that the orientations are compatible when we glue charts together along their boundaries.
Okay, I'm definitely sensing a theme here.
Yeah.
Meticulous attention to detail and a rigorous focus on orientation are paramount in this theory.
Absolutely. Without this level of care, the theory wouldn't hold together. Now, to move toward the final stages of the construction, we need to discuss Thom forms and Thom systems. These concepts are critical in representing certain topological information and ensuring our invariants are well-defined.
All right, I'm ready for the next layer of abstraction. What exactly are Thom forms, and how do they relate to these Thom systems?
Thom forms are special differential forms that represent the Thom class of a vector bundle.
Okay.
Think of the Thom class as a topological invariant associated with a vector bundle.
Okay.
And a Thom form gives us a concrete way to represent this invariant using differential forms.
I'm vaguely familiar with differential forms from calculus.
Yeah.
But this sounds much more advanced. Can you give us a simplified intuition for what these forms capture?
Imagine a vector bundle over a space.
Okay.
You can picture it as attaching a vector space to each point on the space.
Right.
Now, the Thom form is a differential form that lives on this vector bundle and captures information about how these vector spaces are twisted as you move around the base space.
So it's like a fingerprint of the vector bundle's topology.
That's a great way to put it.
And in our context, we are interested in proper Thom forms, which have specific properties related to their support, the region where they are non-zero.
Right.
This property ensures that the integrals we'll define later are well-defined.
Got it. So proper Thom forms are like well-behaved fingerprints that don't create any mathematical messes when we integrate them. Now, what about these Thom systems? How do they fit into the picture?
A TOM system is essentially a collection of these TOM forms,
Okay.
one for each global Kuranishi chart
Right.
that covers our moduli space.
Okay.
And the key is that we need these TOM forms to be compatible with each other
Right.
when we glue charts together.
So it's like having a consistent set of fingerprints for each patch of our moduli space.
Yeah.
And when we stitch these patches together, the fingerprints match up seamlessly.
Exactly.
Okay.
This compatibility is crucial because it ensures that our invariants are well-defined and don't depend on the specific choices of charts we make.
Theorem 3.17 in the paper guarantees the existence of such a compatible TOM system for the moduli space we are studying.
That's a big win.
It is.
It seems like we're laying the groundwork for a robust and consistent theory. Now, before we move on, can you explain a bit more about why these proper TOM forms are so important for integration?
Certainly. When we define open Gromov-Witten invariants, we will eventually need to integrate certain differential forms over our moduli spaces.
Right.
But these moduli spaces are generally non-compact,
Okay.
which can lead to issues with the convergence of integrals.
So we need some way to tame these integrals and make sure they don't blow up to infinity.
Exactly. That's where the properness of the TOM forms comes in.
Okay.
A proper TOM form has compact support,
Yeah.
which essentially means that it vanishes outside a compact subset
Okay.
of the vector bundle.
So it acts like a cutoff function, ensuring that the integrand is 0 outside a bounded region.
Precisely.
Okay.
This allows us to define well-defined integrals over our non-compact moduli spaces,
Okay.
even though the differential forms themselves might not have compact support.
That's a clever trick. So by carefully choosing these proper TOM forms, we can essentially localize the integration to a finite region and avoid any convergence problems.
Exactly. It's a subtle but crucial detail that highlights the level of care and precision required in this construction.
This has been quite a journey already, and we've only just laid the foundation. I'm eager to see how these elements come together to define the actual open-closed Deligne Mumford field theory. But I think we've covered a lot of ground for now.
Indeed, we've established the key ingredients and the groundwork for the construction. It's a complex but elegant framework.
Okay.
And I'm excited to delve deeper into the heart of the theory.
Me too. Let's take a moment to let all of this sink in. When we return, we'll explore how these concepts come together to define the open-closed Deligne Mumford field theory and discuss its profound implications. Stay tuned.
Okay. Welcome back to our deep dive into open-closed Deligne Mumford field theory.
I'm still processing all the intricate details we covered in the first part. It's amazing how much groundwork is needed to even begin defining these open Gromov-Witten invariants.
It certainly highlights the complexity and depth of the subject. But now that we have a solid grasp of the foundational concepts, we can move towards the heart of the paper, the actual construction of the open-closed Deligne Mumford field theory.
Okay, I'm ready for the next stage of our journey. What are the main steps involved in building this field theory?
The paper outlines a very specific construction that utilizes Gromov-Witten theory, which provides a powerful framework for associating algebraic objects to our moduli spaces. The core idea is to define a mathematical rulebook that assigns a chain complex to each nodal Riemann surface. And this assignment needs to satisfy several consistency conditions related to how we glue surfaces together.
It sounds like we're building a mathematical Lego set, where each Lego brick represents a surface, and we have specific instructions for assembling these bricks into more complex structures.
That's a great analogy. The Novikov ring you mentioned earlier plays a crucial role here. It acts like a ledger that keeps track of the energy and genus information of these surfaces.
Right, the Novikov ring helps us manage the topological complexity of our surfaces in the maps. Can you remind us what this energy and genus information refers to in this context?
Certainly. The genus of a surface is essentially a count of its holes. A sphere has genus 0, a donut has genus 1, and so on. The energy of a map from a surface into our space is a measure of how much the map stretches or distorts the surface.
So the Novikov ring allows us to build a mathematical model that accurately reflects the geometric properties of our surfaces and their maps.
Precisely. And the paper meticulously outlines the key properties and equations that this constructed field theory must satisfy.
Right, you mentioned these properties earlier. They ensure that our theory is internally consistent and accurately reflects the underlying geometry. Can you walk us through these key properties?
Certainly. Let's start with the behavior under boundary and interior clutching maps. This property ensures that our field theory behaves consistently when we glue surfaces together. Remember, clutching maps are the operations we use to glue surfaces along their boundaries or at interior points.
Okay, so if we glue two surfaces together, the algebraic objects assigned to the resulting surface should be compatible with the objects assigned to the original surfaces. It's like making sure our Lego structure doesn't fall apart when we connect the pieces.
Exactly. To be more precise, let's introduce some notation. We'll denote the chain complex assigned to a surface by C, and we'll denote the clutching map that glues surfaces 1 pound and 2 pounds along a boundary component by C.
So C, he pounds, and C, 2 pounds are the chain complexes for the original surfaces, and C is the glue that connects them.
Precisely. Now, this property states that there should be a chain map, a specific type of map between chain complexes from the tensor product of C, 1 pound, and C pound, where C is the surface obtained by gluing 1 pound and 2 pounds together using...
Okay, so we're using chain maps to ensure a smooth transition of the algebraic objects associated with our surfaces when we glue surfaces together.
Exactly. And this chain map should satisfy certain compatibility conditions related to the composition of clutching maps. Essentially, if we glue multiple surfaces together step by step, the chain maps should commute in the appropriate sense.
So it's like saying that the order in which we glue the surfaces shouldn't affect the final outcome. The result should be consistent.
Precisely. The behavior under interior clutching maps property is similar, except we glue surfaces at interior points instead of along boundaries. The underlying principle remains the same. A chain map should represent this gluing operation consistently.
Got it. So whether we glue surfaces along their boundaries or at interior points, our field theory needs a mechanism to manage these operations while maintaining the algebraic structure. What about the other properties?
Right. The next crucial property is compatibility with the forgetful map. This one ensures that our theory handles the process of forgetting marked points on our surfaces correctly.
You mentioned marked points before. Can you remind us what they are and why we might want to forget them?
Certainly. Marked points are simply special points we choose on our surfaces. They help define Gromov-Witten invariants by specifying where maps should send certain points. Think of them like pins anchoring our maps to specific locations.
So they give us control over the behavior of the maps. But why would we want to forget them?
Sometimes it's beneficial to forget these marked points and consider a broader class of maps. For example, if we study curves passing through 2 points, forgetting 1 point allows us to analyze all curves passing through the remaining point, potentially revealing hidden connections between different invariants.
It's like removing constraints to see the bigger picture.
Precisely. The compatibility with the forgetful map property ensures our field theory respects this operation. Let's denote forgetting a marked point on a surface by pay. So by pay is the surface with the marked point removed.
So acts like a removal tool for marked points. How does the compatibility work?
This property states there should be a chain map from C to C, and this map should be compatible with the composition of forgetful maps.
Meaning, if we forget multiple marked points in stages, the chain maps should commute accordingly.
Exactly. This ensures the algebraic objects assigned to our surfaces transform consistently as we forget marked points.
Got it. So this property ensures a smooth transition in the algebraic structure as we simplify our maps by forgetting marked points. What about the last property?
The final key property we'll discuss is the A-infinity relations. These are algebraic relations that generalize the associativity law for multiplication. They are fundamental in homotopy algebra, which studies algebraic structures up to homotopic concept, capturing the idea of continuous deformation.
Okay, this sounds pretty abstract. Can you break down what these A-infinity relations are and why they are so important here?
Essentially, A-infinity relations provide a way to multiply elements in our chain complexes while accounting for higher-order homotopical information. Our chain complexes are built from differential forms on global Kuranishi charts. While these charts smooth out moduli spaces, they also introduce higher-order homotopical data that we can't ignore.
So the usual multiplication operation isn't sophisticated enough to handle the intricacies of these moduli spaces.
Precisely. The A-infinity relations offer a more refined notion of multiplication that respects the homotopical structure of our moduli spaces.
Can you give us an example of how these A-infinity relations differ from the usual associativity?
Certainly. Let's denote the multiplication in our chain complex by R. The usual associativity law states that A, B, R, C for any elements A, B, and C, but in an A-infinity algebra, this equality only holds up to homotopy. This means there's a chain homotopy, a special kind of map connecting the two sides of the equation.
So the A-infinity relations allow for some wiggle room in the associativity law, as long as we can connect the two sides using a chain homotopy.
Exactly. And these chain homotopies capture higher order information about the moduli spaces. They're like corrections we need to make to account for the homotopical structure.
I see. It's like these A-infinity relations give us a more flexible and nuanced way to handle multiplication in these complex spaces.
Precisely. What's fascinating is that these A-infinity relations naturally arise from the geometry of moduli spaces. The way we glue surfaces together and forget marked points induces these relations on our chain complexes.
So the A-infinity structure is like a hidden code embedded in the geometry of these spaces.
That's a fantastic way to put it. And unraveling this code is key to understanding the deeper connections between geometry and algebra in this context.
This is truly remarkable. The level of detail and precision required to build this theory is impressive. But before we move on, can you tell us a bit more about how these A-infinity relations emerge from the geometry?
Certainly. Let's consider the operation of gluing surfaces along boundaries. When we glue two surfaces together using a clutching map, we are essentially identifying points along your boundaries. This identification induces a new product operation on the chain complexes associated with the surfaces. This new product, however, might not be strictly associative.
So the act of gluing surfaces can introduce non-associativity into our algebraic structure.
Precisely. But this non-associativity is not arbitrary. It's controlled by higher homotopies, which are encoded in the chain homotopies that appear in the A-infinity relations. These homotopies reflect the geometric data associated with the clutching map, capturing how the surfaces are deformed and glued together.
So these A-infinity relations capture the wiggle room introduced by the gluing process, ensuring that our algebraic structure remains consistent despite the potential for non-associativity.
Exactly. A similar phenomenon occurs when we forget marked points. The forgetful map induces a map between chain complexes, and this map also might not preserve the associativity of the product strictly. Again, the A-infinity relations, with their chain homotopies, come to the rescue, ensuring that the algebraic structure remains coherent.
It's amazing how these seemingly abstract algebraic relations have such deep roots in the geometry of our moduli spaces. They seem to capture the essence of how surfaces are glued and deformed, providing a robust framework for our field theory.
Indeed. The A-infinity structure acts like a bridge between the geometry and the algebra, allowing us to translate geometric operations into algebraic language while preserving the essential homotopical information.
This is all incredibly fascinating. But I have to admit, my brain needs a moment to process all of these intricate details.
I understand this is dense material, and it takes time to absorb all the nuances.
Okay, let's take a pause here to let these ideas settle. When we return, we'll dive into the specific construction of the open-closed Deligne Mumford field theory presented in the paper and explore some of its potential implications. Stay tuned. Welcome back to our deep dive. We've laid a lot of groundwork, from global Kuranishi charts to those intriguing A-infinity relations. Now, I'm really eager to see how all of this comes together in the construction of the actual open-closed Deligne Mumford field theory.
Yes, it's time to assemble the pieces we've carefully crafted. Remember, this paper focuses on a specific case involving projective spaces and their real submanifolds.
Right.
The authors leverage all the machinery we've discussed to build a field theory tailored to this setting.
Right. We are finally getting into the concrete details after exploring kind of the abstract framework. Can you remind us why projective spaces and their real submanifolds were chosen for this construction?
Projective spaces, in a sense, represent the simplest examples of complex manifolds. They have a very rich geometric structure while still being relatively easy to work with. Their real submanifolds provide a very natural environment to explore open Gromov-Witten theory as they introduce the necessary boundary conditions.
So it's like starting with a well-understood playground and then adding obstacles in the form of real submanifolds to test our understanding.
A perfect analogy. The construction of the field theory itself involves a few technical steps, but the core idea is to define a symmetric monoidal functor from a category of surfaces to the category of chain complexes over the Novikov ring.
Okay, hold on. Symmetric monoidal functor, category of surfaces, and chain complexes over the Novikov ring. Can you unpack those terms for us?
Of course. Let's start with the category of surfaces. In mathematics, a category is essentially a collection of objects, in this case surfaces, and arrows between them. These arrows represent ways to connect or transform the objects. The specific category we're interested in consists of nodal Riemann surfaces, which are surfaces with punctures and possibly boundaries.
So it's like a family tree of surfaces where the arrows show how we can create one surface from another by adding or removing punctures or boundaries.
That's a good way to think about it. Now, a symmetric monoidal functor is a special map between categories that preserve certain structure.
Okay.
Symmetric means it respects the order in which we combine objects, and monoidal means it has a notion of tensor product, a way to combine objects in a specific manner.
Okay, I'm starting to grasp the level of abstraction here. We're mapping this family tree of surfaces to another category, and this mapping must follow certain rules regarding how we combine objects. What about the chain complexes over the Novikov ring?
That's the target category for our functor. Remember, chain complexes are algebraic objects built from vector spaces and special maps called boundary operators. The Novikov ring helps us keep track of the energy and genus information of our surfaces.
So this functor assigns a chain complex to each surface in our family tree, respecting how we combine surfaces and accounting for their energy and genus. How does it do that?
That's where the global Kuranishi charts and Tom systems come into play. Global Kuranishi charts, as we discussed, smooth out our moduli spaces, which parameterize maps from surfaces to our projective space with boundary conditions on the real submanifold.
Right, those charts are our roadmaps for navigating these complex moduli spaces.
Precisely. We use these charts to define the chain complexes associated with each surface. The chain complex for a surface is essentially the de Rham complex of differential forms on the global Kuranishi chart, corresponding to Alrama.
So we are taking those smooth charts and building chain complexes from differential forms on them.
Exactly. And crucially, we wedge these differential forms with the Tom forms from our compatible Tom system.
Okay.
This step is vital for encoding the topological information of the moduli spaces into our chain complexes.
So it's like flavoring our differential forms with Tom forms to capture the essence of the moduli space's topology.
Perfectly put. The boundary operator in these chain complexes is defined using the de Rham differential,
Right.
which allows us to differentiate differential forms.
Okay, I'm seeing how the puzzle pieces fit together. We use global Kuranishi charts to smooth out moduli spaces, Tom forms to capture their topology, and the de Rham complex to build chain complexes.
Precisely. The amazing thing is this construction satisfies all those key properties we discussed earlier. Behavior under boundary and interior clutching maps, compatibility with the forgetful map, and the A-infinity relations. This really showcases the power and elegance of this mathematical framework.
It's mind-boggling how these abstract concepts harmonize to create a consistent and meaningful theory.
Indeed. Now, this open-closed Deligne Mumford field theory has significant implications for various areas of mathematics and physics, including mirror symmetry, enumerative geometry, and string topology. It offers a new perspective on these fields, potentially uncovering hidden connections.
Can you elaborate on some of those potential connections? Mirror symmetry in particular has always fascinated me.
Mirror symmetry is a profound and mysterious duality between seemingly different geometric objects. It suggests certain pairs of spaces, called mirror pairs, are equivalent in a deep sense, even though they might appear completely different on the surface. Open-closed field theories have already played a crucial role in understanding mirror symmetry, and this new construction could shed further light on this duality, especially concerning open Gromov-Witten invariants.
So this field theory could be a mathematical bridge between these mirror worlds.
That's a beautiful way to put it. Exploring this bridge could lead to new insights into both mirror symmetry and the geometry of these spaces.
Wow, this whole construction is truly remarkable. The level of detail and the intricate interplay between geometry, algebra, and topology are awe-inspiring. What are some of the open questions or future directions that you think are particularly exciting in this area?
There are many avenues for future research stemming from this work. One exciting direction is to explore the higher genus open Gromov-Witten invariants in more detail. The paper primarily focuses on genus 0 invariants, but understanding the higher genus invariants could unlock even deeper connections to mirror symmetry and enumerative geometry.
That makes sense. We've only scratched the surface of this rich theory. Are there any other specific aspects of the theory that you think are particularly ripe for further exploration?
Another interesting direction would be to generalize this construction to other settings beyond projective spaces and their real submanifolds. The techniques developed in this paper could potentially be adapted to study open Gromov-Witten invariants in other geometric contexts, leading to new insights and connections between different areas of mathematics.
It sounds like this field is bursting with possibilities. It's been an incredible journey diving into the world of open-closed Deligne Mumford field theory. Thank you for guiding us through this intricate landscape.
The pleasure was all mine. I always find it exhilarating to explore these profound ideas and see the power of mathematics to unveil the hidden structures of our universe.
Indeed. And to our listeners, thank you for joining us on this deep dive. We hope you've gained a newfound appreciation for the beauty and complexity of this fascinating field. Until next time, keep exploring.